Hello everyone. Welcome to the second session of AI for Social Good workshop. Let me start directly by introducing. I have the first keynote talk of this session by Timo Roos. He's the lead instructor of the Elements of AI online course. He teaches data science and AI at the University of Helsinki, and he's also a leader of the AI education program of the Finnish Center of AI. His research focuses on the theory and applications of machine learning. He has held visiting positions at MIT, the University of California, Berkeley, and University of Cambridge. He was nominated one of the World Summit's AI Top 50 Innovators of 2020. He also serves on the steering group of the Government of Finland's AI 4.0 program and the advisory board of 100 Brilliant Women in AI Ethics list. So without further delay, I'll hand it over to Timo.
Thank you very much, Arpita, and good morning or good afternoon or I don't know, good night, I guess, to anyone attending whichever time zone you are. I'm very happy to be here in Japan, I suppose. Although, of course, physically I'm here in Helsinki, where we have beautiful white snowy winter weather right now. And we're going to go, enjoying that with my research group and sledding down the hill a bit after this. But before that, of course, we have this brilliant workshop, and I'm again very honored to be invited. I will share my screen. Hopefully, we won't have any problems with that. It's always exciting to deal with these things, but it seems to be working, I think. Arpita, is that good? She's nodding. Thank you. Okay, so I really hope that we could have had this live, so we could have had maybe more interaction. I really do miss those, the live presentations. This is actually my first conference talk, although I've been teaching a lot, of course, through Zoom and other things. But I don't know what is the best way to support interaction. I think we have the chat here. So in case anybody wants to, interrupt, I usually say that just, shout up and ask for the floor and ask any questions that you might have. If we were live, but now that we're not, we'll just have to make do. So feel free to use the chat, for instance. I guess that's doable. You have access to that, I hope. And if not, Arpita will instruct me how to get your questions. Okay, so my name is again Teemu Roos. I'm here in Helsinki, and I. As I was introduced as the lead instructor of the Elements of AI online course, and I'll explain in case you haven't seen that or heard about it before. I'll introduce what the heck that might be in the first place, and the overall topic and the overall sort of agenda and my sort of aspirations are towards AI literacy. So offering anyone the chance to take part in the AI community, or at least sort of the discussions around AI. So that's what I'll be talking about. Okay. So let's get going. I think I was given about 45 minutes and some questions. So we'll aim at that. In case you're not sort of worried about spoilers, if you don't want to keep the suspense until the last minute, here's a spoiler. I'll spoil and I'll tell what I'll be saying in the coming 45 minutes, anyways. So there's basically 4 things I'll be saying and describing what I think, first of all, is AI and what it isn't. And above all, I'll be saying that it's not something that's only going to be relevant in the future, some sort of funny or even scary robots. I used to go around giving talks about that the headline was "Forget about the Terminator," but that apparently was a very bad idea to make people forget about something to put it in the headline. So I won't even mention the thing that I just mentioned. So the point being there, not to sort of dismiss. I love science fiction, and also I'm not against that in a way at all. But I'd really like to sort of I would like to have people think of Google search or social media first thing when they hear about AI, rather than scary robots. So that's one thing I'll sort of trying to be steering and sort of discussing how together we can all steer the discussion towards more relevant instances of AI in our lives and in our societies. And with that, I will motivate the argument that when we're now building social good, when we're building AI for social good, it is most often not a technical problem. It's not that we'd have to solve a mathematical or computational problem, or get better data. It's really more, and above that, a political question about setting the objectives and ensuring that everybody's voice is heard in an equal manner, and so on and so forth. So these questions that really determine how our societies are going to react and be impacted by AI are in my view more political than technical. Of course there's technical problems. I work on those technical problems day in, day out. That's my day job, basically, but as a computer science professor. But I'd like to argue that the reason why we need that inclusive discussion around AI, where everybody, not only technical experts, are present, is the political side of things. And of course, I won't go into party politics. I won't go into the there's a lot going on in politics right now, and I'm sure many of you have hard time focusing on technical conference talks when we have our other eye focused on what's going on and what's happening in the news. So I'm not going to go to sort of that sort of political things. I'd rather sort of say that it's policy things, so things that are related to the governmental and other policies that AI governance. So that's the second point. And then I'll actually basically start with showing how we can discuss these complex systems with people who are not technical experts, by showing the underlying principles, and I'll argue that they are actually rather simple. They're more simple than people sort of maybe sort of have realized and like to say. So there, there's this need for people to complexify or make things appear more complex than they are. And the sort of the whole the bottom line or the punchline is that that we'll need AI literacy, so anybody to be able to be critical, to learn about AI, for this more equitable and ethical AI development and applications. So that's the kind of conclusion that I'll be sort of working towards and sort of arguing for. Okay, so that's the spoiler. But I hope you'll be sort of listening even after this. Okay, so I'll start by sort of referencing something that I very much appreciate, not that I have nothing to do with. This is by somebody else, called a person called Arvin Narayanan, who wrote this. Yes, do you have do we have a question? I hear something, or maybe that was just.
No, go ahead.
All right. Okay. Right. So I wanted to sort of give a sort of shout out to people that have been working to resolve some of the mysticism, some of the sort of myths around AI. And there's this brilliant presentation by Narayanan, called "How to Recognize AI Snake Oil," and you'll find that by just googling for that text. And he argues that there's a lot of hype, there's a lot of sort of misconceptions that are, some of them are, of course, sort of accidental, because it is, it's a relatively new field, AI altogether. So none of us has studied that at school, so we don't have the basics. So it's really sort of, we don't have the common ground, the common language to discuss it. But then there's also sort of an incentive in, especially in business, when people are selling something, to hype it up and label things AI whenever it's in their best interest, and that's not always sort of constructive towards AI literacy. So if anybody has missed that, I recommend to look it up and browse it through. I think it's really really good points there, good examples too. Another sort of instance of this, how these misconceptions are, arise, is this kind of quip that goes around in Twitter, and I've been sort of, this is the first and the earliest instance that I've been able to find, attributed to someone called Baron Schwartz. I don't know who that is, but somebody called Quincy Larson tweeted that and attributed it to them, saying that when you're fundraising, you'll call it AI. Suppose you're a company or a startup fundraising some venture capital, you'll say, okay, we're an AI company, we're developing these AI solutions. But when you're going to be hiring people, you're going to be more accurate about which type of AI, whether it's rule-based, whether it's some optimization algorithms, or indeed machine learning. So oftentimes these AI startups, they'll be hiring people with the requirement that these are machine learning experts, so ML machine learning. And indeed, to me, the funny part about this is that oftentimes when you go to these companies, when you ask the people working there as data scientists or data engineers or developers, and you look at the kind of the core component of what they're working on, even if it's going to be sort of some quite complex system altogether, the core component might be something as classical, established, and simple indeed as linear regression. And I actually sort of, some people think that, okay, well, people are dishonest and they're they're lying when they're saying things like that, when they're labeling linear regression as AI. People get a bit frustrated about that sometimes, but I would actually not sort of, I'm pretty liberal in terms of labeling things AI, because we don't, after all, we don't have a good definition that we generally agreed upon. So I think it's sort of acceptable that when you're talking about something that is sort of AI, I'd like to say that it's not like there's not a clear and crisp line between AI and non-AI. I think it's like degrees of AI-ness. So something is more AI and something is less AI. And I think linear regression is to some extent AI, because it's a part of machine learning, and machine learning is a part of AI. Although, of course, linear regression is also a statistical technique that has been used and developed and studied centuries before we even had computers. So in that sense, this, the way I see this, and okay, if you're debugging, it's printf. That's just that's for coders. That's for geeks. Just printing out stuff is a good tool for debugging. But the idea in this, why I mentioned this Twitter joke, is that I think it's oftentimes perfectly fine to talk on different accuracy, different resolution. You don't need to say which AI techniques you're going to apply when you're fundraising or when you're marketing. People wouldn't understand if you're saying, we're a superconvective machine company, or we're a decision tree company. People would be completely confused by that. So in that sense, it's not dishonest to say some things like that, but it's confusing, and that's the issue. And there's a lot of hype, so people are really excited about AI. You know, I'm sure you've noticed that. And there's a lot of people who want to sort of identify themselves as AI individuals, people who are, you know, represent AI somehow, who are part of the community. but then there's this, you know, I've found that there is some truth definitely to this this cartoon that I also found on Twitter or LinkedIn, wherever it was. A lot of people love AI and sort of want to identify as AI people, but then when it comes to actually learning about it, the enthusiasm is not the same. And then, of course, you know, if you're sort of asking, you know, what do you want to learn Python? You know, do you want to learn programming? Then it's even less so. My point of view is that people don't necessarily have to learn programming to learn AI, to learn to understand AI, because, you know, after all, AI is, you know, the systems that are developed and deployed are so complex that it's never a single person developing it from scratch to production. So it'll be a team effort anyway, and it's perfectly fine if there's a bunch of people in the team that have never written a line of code in their life, and that's completely productive. That's completely okay, and I think even sometimes that might be the best way to do it. You know, I don't think it would harm ever if everybody knows programming. I think, you know, it's never going to sort of make people sort of less adapt and less sort of suitable for developing AI methods. So I think it's, you know, anybody should, you know, write a few lines of code at least, just to be able to sort of converse fluently with the members of the team that are going to write the code. So I think that would be actually better, but the fact is not everybody can code, and I think it would be the worst solution to say that, okay, those who don't code at all are not allowed to be in the team, and I think that would be completely sort of backwards. So this is sort of why this is kind of the motivating part of what we're trying to go against and sort of solve. That people would be sort of more eager to learn about AI, and they'd be, you know, enjoying it, and then be able to take part in the discussions. So okay, yeah, I've got this slide. How to explain it to a 5-year-old? Okay, disclaimer here: I haven't actually tried explaining it this way to a 5-year-old. I have tried to explain what AI and robots are to a bunch of 5-year-olds, but I didn't use this method. So you know, let me know if you end up trying it. So okay, now so I don't really know exactly what the background of the you know, you people who are attending and listening to this. So for some of you, this is going to be like really simplistic, and you know, you'll be sort of falling asleep almost. And sort of I hope that for some people this is going to be sort of something that at least is worth refreshing. But I would recommend that even if you're completely familiar with how the nearest neighbor classifier works, you'll maybe take this as a lesson or a proposal, my view, on how to explain it to other people, how to explain it maybe to 5-year-old people. So I hope, you know, you'll be able to get something out of this, even though you might be familiar with how it works. And anyway, so I do this every time I'm given a chance to talk to any audience, basically, except in a sort of, and you know, if I go to, you know, machine learning technical conference, I don't do this. But if I talk to people in other fields, you know, I don't like to say non-experts, because everybody is really an expert in something, right? So, but if I talk to people who are not experts in machine learning, I will give this. If I have 10 minutes of time to put into this, I'll do that. So this will take 10 minutes. I'll just double check that. The time, it seems okay. So I will give an example like this, and so this is how I'll explain how AI basically works, how one AI method works. So, and I will give this example, and then I'll come up with some sort of domain where this data might come from. So I'll say that, okay, here's a bunch of data, and I'll say that these are maybe the example that I often use, that is that these are lakes. So we're biologists, and we're studying lakes, right? And we're studying how Finland, the land of 1,000 lakes. So we're studying the condition of those lakes. And there's a thing called, I was told by people acting, the actual biologists, that that the technical term is eutrophication. Eutrophication, and eutrophication means that there's a growing amount of algae and other, to use the technical term, stuff going on and growing in the water that degrades the water quality. You wouldn't like the water to be, or the lake to be, eutrophied or eutropifying. Okay, and we'll mark those lakes as red dots, or I suppose brown dots in this chart. And the lakes that are in better shape, that are not eutrophied, they're marked as yellow dots. Okay, and this is this chart is this, it's a scatter plot, where the horizontal axis, left right, is the amount of water that flows through the lake, let's say per day. How many cubic meters of water flow through the lake per day. Okay, and on the right, the lakes, I don't know if you see my pointer, but if you do, the lakes here that I'm sort of hovering around are the ones where the flow rate, the amount of water flowing through the lake per day is higher, and on the left, the water is not flowing so rapidly. Okay, and then there's this horizontal axis up and down, and the lakes in the upper range, in the higher up in the chart, these are lakes that are deeper than the lakes towards the bottom of the chart, which are more shallow. Okay, so that's the depth of the lake on the vertical, on the y-axis, and the flow rate again on the horizontal, or the x-axis. Okay, higher flow in the right, lesser flow on the left, and shallow in the bottom, deep at the top. And again, eutrophied being the red or brown lakes, and then non-eutrophied, so in better condition, good water quality, are the yellow dots. Okay, and now at this point, I would ask the audience, I wish we could have maybe a vote or something. Let's see, I think there's the way to for you to react on Zoom. Let's see, maybe this will work, maybe not. But I'd ask you to put a thumb up if, okay, so there's a thumb up. Okay, so that actually works. Nice. Okay, and now let's use that. Let's reset that. Put your thumbs not down, but hide your thumbs for a moment. And if you think that the star on the left, you'll see a star on the left that is not colored, that is a lake for which we don't know the eutrophication status. We don't know whether it should be colored red or yellow. Put a thumb up if you think that it should be colored red. If you're, as I said, you're now a biologist, so if your expert biologist opinion is that the left-hand side lake, the star, should be red rather than yellow. Okay, I see a few thumbs up. Okay. Can we get more reactions? Thank you. I'm seeing Francesca, Arpita, Sandeep, Teresa, Umang. Thank you. Okay, now the other way around. How many of you think the star on the left, should be yellow, that it is not eutrophied? Put a thumb up if you think it should be yellow. All right, and remember to remove your thumbs up if you forgot that to take them out after the last red thing. So if somebody thinks that the star on the left should be yellow, put a thumb up. I see there's a wait. Yeah, I think Lucy has some reaction. Do you want to comment on that? I thought you saw you waving a hand, or just thumbs up, or just saying no. Okay. Okay, she's saying I can't get rid of the thumbs up. I know the feeling. All right. Okay, and then let's do the same on the one for the one on the right. So there's a star towards the right. How many of you think it should be red? Thumbs up. Anyone? I don't see any. How many of you think it should be red? Should be yellow. I'm sorry. Should be yellow. The star on the right. How many of you think should be yellow? There's quite a few thumbs up. All right. Thank you very much. It was nice to get these many reactions. And I see you're using the chat and having a good time. Excellent. Now, at this point, I would ask the audience, why did they choose red on the left and yellow on the right? And I guess in the interest of time, I won't now ask that. But I can tell that I will always get two different answers. And most often the first answer is that because the dots around those stars are of that particular color. So on the left, the dots around the star are mostly, or they're all red, and on the right, that the dots around the star are yellow. Okay, that's the first answer. And then I get another answer, which sometimes I get first and sometimes the second. The order changes, but these two answers I always get. The other answer is that somebody says that, okay, I was looking at those dots and I would sort of infer that the flow rate has something to do with the eutrophication. And the higher the flow rate, so the more to the right the star or the dot, the more likely it is to be yellow. Okay, and that's actually funny because I get these answers, every time. No matter if I'm talking to, in a school to kids, or if I'm talking to, marketing professionals or, board professionals or politicians, I always get these two answers. And that just shows that people, even if they're not trained to, and even if they haven't studied machine learning, they will be able to recognize the basic principles of not only one, but two different machine learning algorithms. Because the first one, where you look at the dots around or the nearest data point, is the nearest neighbor classifier. And that's actually, if we now go and run the algorithm, now I ran the algorithm, and the nearest neighbor algorithm, as you might know, it just chooses the nearest data point and it mimics the color, it copies the color from that. It copies the classification, the label from that nearest data point. That's all there is to the nearest neighbor classifier. Yeah, so that's one thing that people understand without never hearing about the nearest neighbor classifier. And the other one, where you say that, okay, eutrophication, this horizontal axis variable, seems to be the one that matters, and the depth doesn't seem to matter so much. So that has that has basically zero weight on the matter. That's the linear regression, or the, let's say, to be more accurate, logistic regression method. A linear classifier that says the more right you are, the more likely it is to be yellow. And so people, it's actually sort of, in my view, this is proof that it's really something that people can understand, no matter what their background. Okay, that did take 10 minutes. Okay, so that's the method that I teach in machine learning, and the basic principle to whoever I am talking to. And it seems to work, and it sort of, the point is, of course, that I don't want people to start applying this in their everyday life, or I don't necessarily want people to develop this, start writing code where this is implemented, even though that might be useful in some cases. The point is that people will understand that you can do this, and you can understand how it works, and by that you can understand its limitations and its power. So then I will sort of usually sort of show examples of how you can apply this in some sort of practical applications of AI. And of course, if you've played around with this kind of algorithms, you'll know that every one of them has some pros and cons. So that's why we're going to need thousands of different algorithms so that we can choose the one that better sort of fits the purpose. So, for instance, the nearest neighbor algorithm is, it's the good sides are it's simple and it's very accurate if you've got tons of data. But if you've got tons of data, then it becomes very slow. Okay, so there's all these pros and cons, and and there's a formal mathematical theorem called the no free lunch theorem that says there is no best algorithm for all purposes, and that's kind of that's the fine detail. But the bottom line is that these kind of things, these are the basic principles, or these type of principles are behind almost all machine learning algorithms. Okay. So I will show them that you can, for instance, you can develop an algorithm, or you can actually apply this very same algorithm on recommending products in an online store. So we won't go now through this, but we'll say that, okay, we've got this customer Travis who has a shopping history of green tea, t-shirts, sunglasses, and flip-flops, and then we'll compare this shopping history to the shopping history of all these other customers and count how many products are shared between them. So between Sunny and Travis, there's, for instance, I think, what is it? Oh yeah, sunglasses. That's the only item that they have in common. So you'll get one. That's the similarity. That's how near Travis is to Sunny. And then you'll calculate that for the others, and you'll recognize that, okay, Ville seems to be the nearest data point. Okay, you can think of that as the dots and the legs, in the chart. How near they are is now measured to this counting how many products they have in common. And then the label, the purchase, the recommendation here would be now corresponding to the color in the previous slide in the chart with the legs. So the color now corresponds to the label, the product, the recommended product, and indeed we're going to recommend sunscreen to Travis. And again, the point why I do that and why I use this example, for instance, is that I don't want people to be thinking of, well, what should I buy from the store? Of course, you don't start thinking like that and comparing your, receipts and, other people's shopping baskets to yours. Not that, but the point is that you'll understand that if you look at such a method and what it recommends, you will think of, you might think that, oh, wow, the algorithm somehow understands my human needs. Look at Travis. He's bought a t-shirt, sunglasses, and flip-flops. And if he is recommended sunscreen by an algorithm, he might think, oh, gee, the algorithm understands that I'm actually going on a holiday somewhere where it's sunny. I'm not going to obviously need sunscreen here in Helsinki where it's snowing. But if I've already bought t-shirts, sunglasses, and flip-flops, I'm at least preparing to go somewhere warm where there might be sun, and I don't want to get skin cancer, so I want to apply sunscreen, right? And Travis might think, if Travis knows nothing about these algorithms, he might think, oh, gee, the algorithm somehow understands me. It's some sort of an entity behind the curtain. But if you look at that, that little data, the only intelligence there is Ville's intelligence. Ville has bought the same items and then sunscreen. The algorithm is just, tapping into that intelligence by intelligent behavior by Ville, right? And that the algorithm is really stupid, but the behavior that arises from it and the data together is intelligent, and that's what I'm sort of trying to explain to people. And these are my recommendations. That the algorithm obviously has understood me because, as I said, I like science fiction, and I can also tell that I like coffee. So there you go. If I didn't know what's behind the curtain, I would think, oh, gee, this is some sort of, generally intelligent being that has sort of emerged from somewhere. Okay, and that might be spooky. That might be scary. So at that point, I would have sort of been able to explain, and I'm sure to you, most of you, At least this is not news. This is something you were well familiar with. But you know, if you want to sort of take something out of this, take this as a sort of a means, as an argument to explain to people that it's not rocket science, doesn't require any sort of fancy pants quantum computing or different programming languages. If you know how to program, you'll know how to write the nearest neighbor algorithm. It's about 6 lines of code or so. But on the other hand, you'll understand through this example that due to its simplicity, due to its reliance only on the data, on the intelligence of people producing that data, it'll work. And if it's garbage in, then it's garbage out. And people will understand that if they, you know, think of the algorithm, how simple it is. So it's not alchemy, it'll not turn anything into gold, and it's not that kind of snake oil that would cure every illness. Okay. And then I will sort of, I will skip this by most part. You know, if you look now at the algorithms, you will see how ridiculous the forecasts and the kind of predictions of the future of AI have been in the past. And I would argue they continue to be today. So I think this, if people sort of take that attitude and they say, you know, it's a simple algorithm, it still works as long as there's intelligent behavior in the data that you can tap into. If there's repetitive pairs of inputs and outputs that you can solve the problem with, then it'll work. And if not, then it won't work. And then you'll be able to sort of cut through some of the hype and some of the sort of mysticism around AI. And that's the goal. Of course, you can also identify, you know, as I said, the limits, what it can't do, or what can go wrong, even if it works in the technical sense, right? So there's a lot of discussion about the risks related and the issues related to being able to predict individual behavior. And now, since we're here and I have you guys with me, I would actually like to sort of make this interactive, and this is what I'd like to do overall, because after all, I have a certain background. I'm a computer scientist. I can only think of things from my own point of view, and you guys bring in your points of views, and that's what I'd like to exploit by asking you to now think, or maybe after this session, think what kind of risks are involved in algorithms that are able to better and better, when we get more and more data, predict our preferences and our behavior, how we react, for instance, to certain type of marketing or certain type of, you know, attempts to manipulate our beliefs and behavior. So I'd like to for you to answer this question, and there's an URL. I think I'll be able to write that in the chat to say CKBMC0. That's the last one is 0. That there's a link now. I hope I got it right. If you go there, there's a Google form with this one question. I think I wrote it in Finnish, but that's just good because you'll learn Finnish while you're doing that. The question is that anyways. I think it's both English and Finnish. But the question is, what kinds of risks of unintentional or intentional or unintentional harm can result from the capacity to predict individual preferences? Okay, because you'd think that by and large that's a good thing. You can predict how people react, so we can recommend good products. I love Spotify. I like listening to good music, and it keeps recommending me music that I like, so it works, and that's a good thing. But what can go wrong is another question, and there are things that can go wrong, and I'd like to collect people's points of view, and that's why I have this Google Sheet. I've collected this from a few dozen talks that I've given, and it's really sort of interesting to read people's answers. And now that I have you here with me, I'd like to sort of exploit that same thing. So if you write that down, that URL, and you'll think about it for a while, and then you'll submit just a one line of text or whatever, it's going to be fine. No need to be a full essay on this topic. Of course, if you've written an essay, you can give me the pointer to that. I'll be happy to read it. Okay, so that's the that's the motivation, and now it's high time okay, here it's just some issues that I've gotten before, but let's not maybe go through them. Let's go to the elements of AI. That was in the title. I'm sure you've been sort of wondering what was that if you haven't seen it. So Elements of AI is a free online course in 6 acts. That's Winnie the Pooh type of description, in which we are introduced to AI and some of its implications, and then the stories begin. Okay, so this is a collaboration between my employer, University of Helsinki, and a Finnish IT consultancy or IT company called Reactor. And now we started just like pro bono. We started thinking, okay, we'll raise awareness of AI in Finland, and we'll create this resource just for the heck of it. But then more recently, we've been sort of gaining endorsements and support by the European Commission and the government of Finland. And we launched in 2018. Globally, and then we did a Finnish language version, so the flags here are different countries' versions, and for each country we do the local languages, so that we don't even, there's no barrier for people to take part. So we've now into something like 15 different countries. Croatia and Italy are the most recent. And it's, we're highly rated, and we're happy about that. Even more happy we're about the fact that just today, I looked at the statistics, just today, it's the first day when we went over 600,000 registered users just this morning. And the thing I'm most happy about is that how diverse the crowd is. So this is for everyone. It requires no maths or programming skills, and we've got almost 40% female. In fact, in the Nordic countries, it's above 50% female users. And we've got something above 20% over 45 years old people. So it's not like students that I, of course, normally teach at the university. So this is sort of people in the working life. The oldest have been 80 or even over 90 years of age who have taken the course. And we have now a follow-up course also, because people really asking for that, asking for what to do after the Elements of AI, the first part, and the second. So the first part is now called Introduction to AI, and the second part is called now Building AI. And there are some optional programming exercises that's sort of addressing the who wants to learn Python part. Okay, so there's some fun things that you can do with a bit of Python code, and you'll sort of feel that, okay, well, it wasn't that hard. You'll get those bragging rights. I wrote an AI algorithm over the weekend. What did you do? I can sort of see a lot of CEOs being just about those bragging rights. So we'd like to invite anybody to be a member of the crowd, member of the community, and work in and manage AI projects and participate. So making people turn from AI consumers to AI contributors. That's the kind of the punchline. That's the sort of ideal that we'd like to reach with this course. We launched last October, and we've got almost 10,000. I didn't look up that number this morning, but it's sort of close to 10,000 registrations and above 10% completion rate, which for an online course, I'm quite happy about. So I seem to be sort of short of time, but I'll just sort of point to a few things about the design and the impact of these courses, how we've sort of been able to reach that ideal of inviting people to take part in the discourse and sort of not be afraid of AI. So we did by, the pedagogical style, there's no magic there. It's really kind of old school. There's no video at all. There's no kind of fancy, no fancy business. It's really text and illustrations, and the careful design of the exercises so that they challenge but also reward in a sort of you know, in a way that the learning curve is sort of supporting one's learning. And we also wanted to, the visual style, we sort of, as you could see from the illustrations that I used, it's kind of visually friendly and easy to approach. And not, if you do Google image search, you know, if you haven't done it, just go try it. Go on Google, go and do the image search with AI as the search term, and you'll see only one kind of thing: blue wire brains. That's nothing but that, or these white humanoid robots. So we don't want to look like that, because that's not, you know, that's not what everybody sort of feels comfortable with. And we built a community with peer reviews among the students and these discussion forums. And we've done a lot of effort to push this on the EU level and globally, and getting, you know, presidents and you know, VIPs, but also sort of local people, you know, book clubs and libraries to help people find it, because, you know, not a lot of people are actively searching for AI courses online. So we'd like to sort of fix that, and we've got a lot of success. One thing, again, as you know, I'm very happy about the gender balance. So we've got 50-50 in the Nordics in the course, and I think that is somehow reflecting at the University of Helsinki computer science admissions that have been sort of, you know, the number of female students applying to study computer science with us has been sort of almost doubling for 3 years in a row. So it's now sort of 30%, and I hope that it will keep growing. And a lot of people say that this has changed their thinking about AI and sort of help them understand the discussion, and that's the goal. Oh, just final thing. I'll wrap up here. I will have a few questions. I'll point to another course. This is not, I haven't been involved in the creation of this course except in a sort of a minor advisory role, but there's other people that are at our university who created an ethics of AI course, which you'll find at ethics-of-ai.mooc.fi, or if you Google for ethics of AI MOOC or ethics of AI Helsinki or whatever, you'll find that, and London and Amsterdam have been involved in that as well. And that's kind of the same visual style, same sort of easy user interface. You can do it on the mobile or your laptop or whatever. Anyway, I think I went 5 minutes over time, but that's it. That again, my points that I wanted to convey to you today. So now I think you know, anybody is free to unmute themselves or raise a hand or write a. If you don't want to do that, you can ask a question on the chat, and I'll be happy to answer. I think we have, you know, 5 to 10 minutes. Arpita can confirm.
Yes, we have like 10 more minutes for question answers. So you can either write or just unmute yourself and ask the questions directly.
Yeah, that'd be great.
I think Seku has a question. You want to unmute yourself?
I was saying that was a round of applause, but I can ask a question.
Okay, thank you very much. I appreciate that. And a question is always welcome. Go ahead.
Okay. So the question I have is that it's interesting to look at how people without domain expertise may be able to interpret, or at least appear to be able to interpret algorithms that are pretty useful or all-pervasive. One of the questions I have is, do you think that there's enough study on how people might get the understanding of algorithmic output wrong, meaning the misperceptions?
Mm-hmm. I don't know. If anybody else has a good answer to that, you know, if there's studies about how people misunderstand AI, I think that'd be highly appreciated. The only thing I know is that people have studied maybe not individual algorithmic outputs, but the overall perception of AI. So there's this work, I wish I remembered who it was by, but there was this work that I just recently bumped into on the misconceptions and the sort of misrepresentations of AI as as an agent, as an entity, rather than a tool. And there are some studies on that in the more, let's say, philosophical literature. But that's a really interesting question, and I think a lot of social scientists have a lot to say about how people interpret and maybe sometimes misunderstand AI. I hope that answers. Okay, so thumbs up. And Teresa was asking if we're collecting comments or reactions among people attending your course or our course, of course. Well, we have a lot of feedback through various channels, through like directly on the discussion forum that we maintain and operate and set up. We've got a lot of people giving us feedback on Class Central, which is a kind of a guide or review platform on MOOCs, and so. But maybe we're not sort of maximally structured or systematic in collecting that feedback. We are planning of running an impact study, doing before after questionnaires in the population to see whether we're able to turn the impression of people of AI. And to that, I'd like to say that we're not aiming to turn people's opinion or attitudes more positive about AI. There's a lot of over-optimism. So for some people, I think we'd need to dial down on the positive, negative aspect of how they think about AI. I think some people are, we should remind them that, there's downsides too. What I'd like to do rather is to make people more active rather than passive. Right? So not positive, negative aspect. I don't want to sort of meddle with that. I don't want to tamper that. It's not my call. It's people's. That's there for them to decide after having sort of become informed about AI, whether they like the applications of it or the way it is used today. That's exactly the kind of public discourse and political decisions that I don't want to be making on people's behalf. But I'd like to have people sort of more active. So and we're doing those studies, but we don't have the results yet. Francesca was asking or commenting, general theory of uncanny valley. Yes, that's true. And that explained the perception of AI and robot, that more human they get, more scary they appear. But mostly of AI studies depend on the interface they appear. I guess, yeah, that's a good point, Francesca, making about robots. So that when they're like human-like, but not quite right, they appear quite uncanny or unpleasant. And of course, we know from meeting other people that if they'd be perfectly human-like, we wouldn't have anything against that. Maybe except in sort of as an idea of understanding that they're not exactly people. So that is true. That's a good pointer to the attitudes. And we have a question. I'm just keeping the time here. Naoki Fukuta says, how did you notice that some people think the AI understands, in quotes, understands something when they have little knowledge on AI? I completely forgot. Andli, you have told me. Yeah, I think this is some sort of a personal, out of personal experience, out of maybe. I would say that grew, that sort of that feeling and that thinking and identifying that as an issue grew out of teaching computer science students. So even computer science students, when they came to, I've been teaching, for 11 or 12 years, this introduction to AI course at the CS department, computer science department. And even the students who came there, usually second, third year students, bachelor students, they would come to the AI course and they would expect to be, they've watched Star Trek, where there's this Data, this android, and they've watched, obviously the Terminator films. And they come to the class somehow expecting that we'll be studying things like that. And then I'll have to sort of have them unlearn or sort of disillusion them about this sort of understanding part. But I would say that it's not very easy, because if you look, if you look at how people are having discussions about AI even today, you might have seen that OpenAI, this sort of private AI research lab, they came out with a system where you can sort of just write a description of an image or an illustration, and it draws that for you. And it's kind of amazingly cute. You can say that, a crocodile riding a bicycle, on marshmallows or something, and it'll actually draw that, and it'll look sort of convincing, at least if you repeat it a couple dozen times and pick the best. And then, if you do this kind of cherry picking, it'll look very impressive. And people are now saying that this is what understanding means to me. People are saying something like that, and it's really hard to combat that, because other people, kind of trying to work against that disillusionment, and that's yeah, I don't know where it comes from. Why people have this need to talk about understanding so much when it comes to AI, because it's obviously not understanding anything, it's just an algorithm. Okay. Although I'm not a philosopher, I don't know what understanding means, I have to say that. So maybe if we redefine understanding as looking like you understand, maybe it does that. I think we're just about out of time. Francesca had right, how do we ensure that the course attracts and is approachable by female users? I think the goal was there to just look at the visual design and visual appearance of all things AI, and realizing that they are really very homogeneous, these blue wire brains. Even sort of going beyond that, thinking afresh, thinking of, well, okay, let's not go with that. Let's do a more diverse color scheme. Let's do a friendly, solution-oriented, talk about the practical, real-world, everyday applications. I think that seems to be appealing to a more diverse crowd, not only in terms of the gender, but also in terms of the age and other socioeconomic and other factors. So I think it's just, blowing up the established visual imagery and starting fresh. That seems to be doing most of the work. We didn't really design it for women. We designed it for everyone. And I think that seems to be, it's surprisingly easy when you don't just, follow the established way of illustrating things. All right, so that's our time. I think you guys have a long day ahead of you. And I'm also sort of planning to tag along and enjoy some of the other talks. So I wish you a really nice day, and I really thank warmly for the chance to spend this time with you. And I encourage you to send me any comments. You can see my Twitter handle down there, @dem_rules, and there was this questionnaire that I'd really like to hear from you through. So thank you very much.
Thank you so much. It was a very engaging talk and very wonderful. I mean, thank you. So with that, let's go to the next series of some long talks as well as some spotlight talks. And to conduct that, I would invite Shivika. Are you already there?
Yeah, hi.
Yeah, so Shivika is going to chair the next session. She is PhD at Indian Institute of Science, Bangalore. She's also a recipient of the Tata Consultancy Services Research Scholarship. And yeah, I'll just hand it over to Shivika.
Thanks, Arpita. So welcome everyone to the next part of the AI for Social Good workshop. And so now in the next hour, we'll be having 3 long talks and 3 short talks. So we'll first begin with the longer talks. These talks will be about 12 to 13 minutes long, and it'll be followed by 2 to 3 minutes for questions. So you can ask your questions again, but either by leaving them in the chat, or you can raise your hand at the end and we'll ask you to unmute yourself. If by chance there are any questions that are not answered during this time, there's a poster session later today, and it'll be another opportunity to take them up. So without much further ado, we'll go on to the first talk, which is the European strategy on AI. Are we truly fostering social good? And this is presented by Francesca. Francesca, you can start.
Yeah, thank you very much. Can you hear me well? Okay, great. So just a minute. Can you see my screen as well?
Yes.
Okay, thank you very much.
Yes.
Okay, so my name is Francesca Foffano, and I will present you today our research regarding European strategy on AI. So before to start, I would like to say that we are taking part on the AI for EU project. It is a project funded by Horizon 2020. AI for EU is an European platform to facilitate collaboration between all European actors, sharing expertise and research in AI. And in particular, we are taking part in the Observatory of Society and AI, that is a part of the platform where we try to foster the key European values that are, for example, the ethical, social, legal, cultural, and economic issues regarding AI. Inside the site, we, on one side, publish content and articles. On the other side, we try to invite public and private partners to collaborate together through some working group activities. This is part of the entire European vision that is taking shape in those years. So since 2018, there was the publication of the strategic plan, Artificial Intelligence for Europe. In the fall of month, European Commission also create a high-level expert group that helped to create the publication of trustworthy AI guidelines that are a document that contain the 7th value of artificial intelligence for the European Commission. And in 2020, there was also the publication of white paper on artificial intelligence. That is the first effort from the European Union Commission to actually provide a legal framework. Since 2018, actually, European Commission asked to the member states to provide official documents for national strategy and to follow 3 main pillars. The first pillar was to boost the AI through economy, and therefore to also use economy to boost AI. And the second one instead was to tackle such economic change that the AI will bring in the life of citizens. The last one was also to ensure an appropriate and ethical and legal framework. So on those documents, we can already see that the vision of the European Union is to foster a responsible and sustainable AI. But in particular, they want not only to empower and protect individuals, but also the whole society. What we find in the literature is that we are currently dealing with a lot of research that concentrate on heterogeneous guidelines. So they're taking consideration private, public, even nation guidelines. But we wanted to have a more focused approach on how European Union is actually translate those values in a plan and action for the development of artificial intelligence. Therefore, we actually select 15 national strategy, and we make sure that was the official national strategy released by each of the country, and that this document was released in English. And then we try to understand if the effort claim for social good was actually being translated in quantifiable investment. To do that, we did a qualitative analysis to really understand the reason, the meaning behind each investment. To do so, for somebody that is not aware of what a qualitative analysis is, the true researcher was actually selecting some filter to apply to the document and then read the text that was meaningful for us. The researcher then classify each portion of the text with a code that is actually a label that was referring to the content and the meaning of the text. Then the two researchers merge together the code and then create a second order code that is a macro group of the first code order, depending on the similarity or the fact that it was referring to the same topic. Our research filter was, for example, that each investment needs to have a clear estimation in terms of money allocation, needed to be made by the nation under consideration, and also needed to be planned for that year or the future year coming. However, we see that our research has some limitations. For example, some data could be partially present or missing or even described in other documents. We need to take consideration that a lot of documents were released in the same period. That could be like, for example, some action plan or some document from expert in AI that was called by the nation or the country. Therefore, we didn't want to generalize our result and oversimplify representation. We also need to consider that there are not quantity of investment done in our research, so we didn't really look how much has been spent, but more on where it is spent. And in this sense, we can see we try to create a map to the field where nations are more likely to invest their money. So here we have a presentation of our results. On the left side, you can see there are the second order code, so the macro area that those investments are referring to. And on the top, there are actually the nation that was referring to investment in the national strategy. For each colorful square is one investment that was stated in the document. So we also can see the quantity of investment state. As is possible to see, there is not a heterogeneous distribution. However, we will see that more specifically in the next slide. So we actually can define some general trends. So most of the nation was referring to national funds or some kind of package of investment that they wanted to invest in the nation. Some of them was currently invested, some other was planned for the future. However, a little less country was actually taking a step ahead and describe which kind of technology they want to invest in. So some of them was investing in general digital technology, whereas other was specifying the field of interest, like for example, cybersecurity, data security, or even acquire of a new supercomputing. Then, as it's possible to imagine, there was some investment in the private area, for example, in companies, but also in public entities. We have the case of local administration or even investment for academic AI research. A specific case was instead the one provided by Malta, that they wanted to invest in the national promotion of the nation over the European community. And then we actually arrived to social good, that it was our main interest. So as it's possible to see, there are less countries that was concerning about social good, or at least that was actually provide a qualitative amount of investment for social good. So on one side, we have society. For example, Netherlands consider the social impact that AI will have on citizens through our research. And whereas Denmark instead referred to the intention to improve the digital welfare for solution for citizens. Then, of course, we also find some referring to cooperation. So, for example, between public entities, international entities, or even public and private entities. However, the most interesting result for us was education, because we divide education depending on who was going to benefit from it. So some countries refer to employer training. So some kind of courses or upskilling that was already been meant for people that are expert on AI or are working in the field. Whereas other countries are referring to AI literacy for citizens. So the kind of courses that can be provided to citizens to better understand how AI will change their life and how to make them aware of what is AI. And lastly, we also have educational funds that are some investment that has been made for create some course at school or university, or even to promote students in study AI. So from this point of view, we actually see that there are some things going on and there are some movement, but we still see a lot of space for improvement, and we wanted to give our vision or our contribution to these changes. So we selected 4 areas that for us are really important. The first one is social implication. As we saw with the Netherlands, we really believe that it's important to foresee the challenge that society will face with AI. And in particular, because we believe in social participation. That means society should be in the loop of life circle of AI, because at the end, it will affect their life, and they should be able to participate and direct offer the contribution in this process. And this is because we really believe in a global benefit for everybody. And for achieve this goal, we need to have a holistic approach. And this doesn't mean only consider all the actors involved, but also the effect that those investments will have in the life of everybody. Because as the butterfly effect, the investments that we do actually shape the future we will live in. And lastly, most of the countries reported they want to create a legal framework. However, we would like to see more measurable effort in this term to the promotion of ethical and legal AI framework. But also it's really important to consider that citizens should be aware of this legal framework and should be able to assess that and to find support for their rights. So we really believe, we really hope actually that the future of European Union will be able to englobate all the value that actually have been stated. And I will conclude here my presentation, but before to leave, I would like to say as the Observatory team, we are always looking for collaboration, and we are always welcome to collaborate with people that are coming from Europe, but even other countries to actually can progress together. Thank you.
Thank you, Francesca. I think we'll have a minute for questions if there are any. So if you want to ask a question, you can raise your hand or leave it in the chat. Well, I have one question if no one else is asking. So, so I saw that Denmark in particular and even Netherlands had very detailed plans, right, for how to invest the money. So is there some sort of socioeconomic component to that, or I mean, if you looked at that?
So we personally, that was one of the questions that we ask ourselves a lot, like how much we consider like the money that are already circulating and the money that will be invested. Because of course, if they are more likely to invest, it also could be that is giving some profit. Like Netherlands for sure is a great country in terms of research and development of AI. So we cannot prove completely because it will be like another research another time, but we are likely to say that at least those countries are more likely to take in consideration or to be aware of what AI means in their daily life and even in society. So I can imagine that something is moving there that is consistent more than other countries that need to imagine the future of AI because they are not currently living in that.
Right. No, that makes sense completely. Thank you so much.
Thank you.
So we'll have our next talk by Umang Gupta, and he will be talking about controllable guarantees for fair outcomes via contrastive information estimation.
Hi,
Umang, you can go ahead.
can you guys see my screen? Hello?
Yeah, it's fine.
Okay.
Yeah.
Okay, cool. So hi guys, can I go ahead? Yeah.
Yes, please start.
Okay, sure. So hi, I'm Umang, and I'm a PhD student at University of Southern California, and I'll be presenting this work on controllable guarantees for fair outcomes via contrastive information estimation. This work is in collaboration with Aaron, Professor Bistra, and my advisor Greg at University of Southern California. So the problem of unfairness in decision making doesn't need much introduction. I mean, we already know that unfairness of algorithms is a problem, and as we are using machine learning for critical problems like hiring or crime screening or even healthcare applications, it is important to ensure fairness. In fact, a lot of data sets are biased, and it is important to ensure that algorithms do not encode or exaggerate this bias. So in this work, we present a new representation learning algorithm for fairness in classification problem. By fairness, I mean demographic parity. We only focus on this definition. So our work relies on relating demographic parity with an information theoretic term. In particular, we actually show that we can control demographic parity by minimizing mutual information between representations and sensitive attributes. While we show this, that demographic parity can be controlled by controlling mutual information, we then present a variational objective to control or to estimate and optimize this mutual information and leverage some of the recently proposed contrastive mutual information estimators. Finally, we demonstrate that the representations produced by our algorithm are more accurate, and while also providing guarantees or fairness guarantees against any adversarial exploitation. So first things first, I'm sorry, for some reason this Zoom is blocking my screen. Okay. So first thing first, the definition of demographic parity. It is defined as the difference in the selection rate between different groups. So this probability of y hat equal to 1 given c equal to 1 is selection rate for the group which has c1. And so intuitively, demographic parity tries to equalize the selection rate among different groups. And as a result, a perfectly fair decision algorithm would ensure same selection rates for different groups. While we focus on demographic parity, there are other definitions or measures for fairness. And for different applications, different measures may be relevant. However, some of the human studies by previous works have shown that demographic parity closely captures a layperson's perception of fairness. So that's why we think that this is probably the most important definition to focus on. So fair decision making is often categorized by the different machine learning pipeline they modify. For example, pre-processing or representation learning, which is the focus of this work, transforms data such that any downstream or any classification algorithm that acts on this representation is guaranteed to produce fair outcomes. So in this case, downstream users or downstream algorithm will focus on maximizing performance, and the onus of ensuring fairness is on the representation learner. In processing methods modify the learning algorithm itself, and post-processing post-processing methods modify the outcomes of an unfair machine learning algorithm. In this work, we'll focus on representation learning. The main thing to note in representation learning is we need to make sure that representation are fair with respect to any decision algorithm. So as we said that we want representation to be fair with respect to any decision algorithm, but the demographic parity depends on what algorithm is being used. So as a result, one of the most important contribution for this work, or one of the important contribution is that we show that the mutual information between the representation Z and the sensitive attribute C upper bounds a monotonically increasing function of demographic parity. Pi is dataset dependent constant, and we can ignore that. So as a result, bounded mutual information would ensure bounded parity. Moreover, by decreasing the mutual information, we can decrease the parity. And so we translate the problem of controlling parity to controlling mutual information. it is worth noting that some of the previous works have also used this information theoretic quantity. However, for example, however, they do not establish these relations and therefore cannot guarantee the fairness of representations. For example, the work by Song et al. In AI Stats 2019, they evaluate empirical effectiveness of this objective, of this information theoretic objective to control fairness. While the work by Moyer et al. And NeurIPS 2018, they use this information theoretic term to learn invariant representation, and they show applications to fairness. However, with our results, you get guaranteed fairness for the you can guarantee fairness for the representations without making any assumptions on downstream algorithm. So now that we have a way to control parity for any algorithm, or an algorithm agnostic way to control parity, we can discuss the overall information theoretic objective. Other than ensuring fairness, we would like our objective to be informative about the target task Y. This two desired objective can be captured by maximizing mutual information between the target task and the representation. That would capture information about the target task. And then you can also minimize mutual information between the representation and sensitive attributes, and that would control fairness. Beta is a trade-off hyperparameter that would give different importance to this two objectives. And to make sure that the information theoretic quantities are well defined, we assume stochastic representations, and the distribution is denoted by Q of Z given X. In our experiments, however, we find that this objective is not very good, and this is because, or we think that this is because the mutual information between Y and Z conflicts with C and C. As we can see in the information Venn diagram, there is an overlap between these two terms, and which is denoted by yellow color here. We find only via experiments that the mutual information between, or that this conflict is not necessary, and this can be avoided by maximizing the mutual information between YZ given C, that is the green region only, and this leads us to an improved objective. Intuitively, what we are doing is we are trying to capture only the information about data in Z, or only the information about target task, which is not in C. So as a result, we would try to maximize the green region and minimize the red and yellow region if we talk about this Venn diagram. So finally, now that we have an information theoretic objective, the problem is still not solved because it is challenging to optimize or compute information theoretic quantities directly. So therefore, a common approach is to propose variational bounds for this information theoretic objective and then optimize those. So the first term, in the first term, which is the mutual information between YZ given C, it is easy to tackle this term, or it is easy to lower bound this term. Because Y is a binary variable usually, it's a decision variable, so it's Y binary 1-0 variable, or at max a multinomial variable. This can be lower bounded by cross entropy term, and so that's easy to do. The second term, however, is hard to compute, and I think it is very hard to upper bound it directly. So we split it into two different information theoretic terms. We write it as the difference of two information theoretic terms. Once we write it like this, we can compute these two terms, or we can variationally bound these two terms using known bounds. So the first term, which is the mutual information between Z and X, is similar to the rate term in a VAE or the information bottleneck term. And so we directly upper bound it by assuming a prior P of Z. And similar to VAs, we use a Gaussian prior and posterior. However, you can use other distributional assumptions. However, you can make other distributional assumptions too. The last term, which is the mutual information between Z and X given C. For this, we use contrastive estimation and extend the contrastive estimators discussed in Ben Poole's paper to estimate conditional mutual information. These three variational objectives define our whole objective, and we call it fair contrastive representation learner. So now that we have seen the loss function, I'm going to discuss results and experiments. So we evaluate our approach on mainly two standard fairness dataset. The UCI adult dataset is a 1994 census dataset, and the task is to predict predict if the person's income is more than 50K USD. The protected attribute here is gender, and so you don't want the income prediction to be dependent on gender. And in this case, the gender is binary, so there are only two groups. Heritage Health dataset is the dataset of patients with where the task is to predict the 10-year survival of the patients, and the protected attributes are the age groups. There are 9 age groups. We reported results for both these datasets in the paper. However, for this presentation, I would show results from the UCI adult dataset. As we talked previously, for the representation learning algorithm, or for fair representation learning algorithm, the downstream users are going to use any possible algorithm and focus solely on maximizing accuracy. Also, there is a trade-off between fairness and accuracy, and one often likes to find a good trade-off rather than finding a perfectly fair fair representation. So we learn representation by varying this loss hyperparameter. For example, the beta in the loss function I discussed. For other baselines, there are other loss hyperparameters. And then we visualize parity accuracy curve that are produced by classifying these representations. So for the downstream algorithms here, we would use one hidden layer classifier or one hidden layer neural network. However, we did not see much difference in the ranking of our method versus other baselines when using other downstream algorithms. We visualize parity accuracy curve because it's a good way to visualize the trade-off between accuracy and parity, and we would want to prefer a method that gives us a good trade-off, basically higher accuracy and lower parity. So the first thing our approach provides more accurate and fair representations compared to adversarial methods like adversarial forgetting, Maxent ARL, and LAFTR. In fact, we find that these methods do not achieve lower parity at all and are mostly concentrated on the top right. We also outperform, our algorithm also outperform approaches like an information theoretic and non-adversarial approach like CWIB, or information theoretic adversarial approach like MIFR. In the figure on the right, you see the accuracy versus parity curve, and one would like the accuracy to be high and parity to be low, or for fixed parity, you would like to have higher accuracy. Therefore, the points to the right and to the bottom are better. And as we can see, our method, which is highlighted with red circles, is almost always on the right and the bottom. Just a second. Okay, sorry, there was someone on the chat. Sorry. So therefore, we see that our approach provides better, more accurate and fair representation for a wide range of parity. Other than providing more accurate and fair representations, our approach has some more appealing properties that make it useful for practical adoption. For example, one thing is that our approach has a single hyperparameter to control fairness. The baselines we have discussed have more hyperparameters, and therefore therefore cause more overload to incorporate fairness, whereas our method is single parameter and causes less overload to incorporate fairness. Other than that, the beta hyperparameter provides a smooth control over fairness. As we vary beta in the figure on the right, we see that the parity decreases smoothly, as a result, providing more and more fair representation. However, we also see some degradation in accuracy, as obviously fairness and accuracy are at odds with each other. The next thing is parity accuracy curves. So parity accuracy curves are really important as they provide lookup for fairness constraints. And we find that because since our method has a single hyperparameter beta, which can be beta, and mostly because we have a non-adversarial objective, we can vary beta in small steps to achieve beta in small steps and fine-tune the model trained with a separate beta. So this reduces the cost to train different models from scratch. So the points that you see here, the blue points were trained by fine-tuning and required roughly 780 epochs, whereas the red points were trained from scratch and they required more than 6,000 or 8,000 epochs to generate this parity accuracy curve. This brings me to the end of this presentation. To summarize, we showed that by limiting mutual information between representation and sensitive attribute, we can provably ensure fairness of outcomes for any downstream algorithm. We also proposed practical ways to control mutual information by contrastive estimation, and this led to more accurate and fair representations. While we have focused on demographic parity in this work, for future work, we would like to incorporate other fairness measures. For example, equality of odds and equality of opportunities are other popular fairness measures which we could not incorporate under this framework. The code for this work is available on GitHub, and I would be happy to talk about it more during the poster session. Thank you for listening.
Thank you, Umang. I think we have a question here. So yes, so the question is, how dependent is the current curve on the number of runs?
So okay, I think I should share my screen again. So if you see, I compute parity over max over 5 runs and accuracy is mean over 5 runs. So the results do not vary much, but we take max over 5 runs as the worst case of parity, and accuracy is mean over 5 runs as like average case informativeness. However, the runs were not very sensitive to the, however, the results were not very sensitive to runs. I think for 5 runs, the results were somewhat, for 1 run, the results were somewhat noisy, but not very noisy.
Right. And okay, so we have one more question, which is, I would like to ask about the topic of accuracy fairness trade-offs. Recently, there have been a number of people disputing this trade-off in the first place. Yeah. The way that this problem is formulated in this work makes it evident that it does. Do you have a comment on this issue, and does the definition of fairness and accuracy make a big difference on the trade-off?
So the thing is, for demographic parity or how the data set is collected can cause or the data set the data sets are historical and they're often biased. So for example, if you assume that that you have a oracle and a perfect classifier for your data set and you compute demographic parity for that, you would see that your data set is already biased or very likely to be biased. In this case, there would be a fairness accuracy trade-off because as you try to bring down demographic parity, you're guaranteed to make mistakes. However, there are other definitions like equality of odds or equality of opportunity, which tend to not have this kind of conflicts. So it depends on definition of fairness, or some people even ask this question that if accuracy is right thing to measure because your training data set is already biased, and maybe the accuracy is not the right thing to measure. So there are some more works in this direction. Does that?
Right. Yes. I think so. We are a little out of time here, so we'll just move on to the next talk.
Right.
Thank you so much, Umang. And the further discussions can happen in the poster session. So yeah, thank you. So the last long talk that we have will be by Sushant Agarwal, and he will be talking about the trade-offs between fairness and privacy and those between fairness and interpretability in machine learning. So Shant, the floor is yours.
Hi, can you guys see my screen?
Yes, please go ahead.
Okay, how much time do I have? Because since I'm like a little above.
Yeah, so you can take, I mean, I'd say make it as short as possible, but yes, we can eat into the break a little, I think.
Okay, cool. Okay, so hi everyone. Thanks for coming. So this is a combined talk of two papers in this workshop, and in the interest of time, I will omit some technical details, proofs, and also the related work. So as you all know, algorithms are deployed to make like consequential decisions nowadays, and some well-known examples are recidivism prediction, admissions, and loans. And I mean, because algorithms such as these are making decisions that are life-altering for many people, there have been many ethical questions raised about how they function. And the ethical questions we will look at in this talk are fairness, interpretability, and privacy. So, I mean, I'll just give a broad overview since, like, it's been gone, like, people have spoken about this before. So, we'd like an algorithm to be fair and not discriminate against an applicant because of the membership in a minority or protected group, which could be like a particular race or gender, etc. We'd also like the classifier to be interpretable, and what that means intuitively means is that we would like to be able to explain um, how the classifier works and convincingly explain any decisions it might make. Another concern is privacy. So these classifiers are typically machine learning models and are trained on sensitive data. So we not like our classifier to leak information about people in the training set and would like to protect their privacy. Um, so these concerns have received a lot of attention in the research community recently. However, they have primarily been studied in isolation. That is, we have mainly looked at scenarios in which we'd want to satisfy one of these properties at a time. In this work, we look at cases where we want to satisfy multiple of these properties simultaneously. We essentially have two theoretical results. The first one looks at cases where we would like to have both fairness and interpretability. And we show that these properties sort of compete and it is hard to satisfy both of them simultaneously. This result builds on a paper by Kleinberg and Mullainathan. In the second one, we look at cases where we would like to have both fairness and privacy and show, we do have questions in the chat. Okay, no. In the second one, we look at cases where we would like to have both fairness and privacy and show that it is hard to satisfy both of these properties simultaneously. This result builds on a paper by Cummings and others. Okay, so a common method to build interpretable classifiers is to essentially avoid using very complex models such as neural networks, which have like a ton of parameters. Instead, one could use simpler models, intuitively simpler models such as linear classifiers. We consider a framework to model this formally. Then we show that if we restrict our classifier to be simple within this framework, it can be replaced by a more complex classifier that strictly improves both fairness and accuracy. Hence, we see that in a sense, interpretability or simplicity in this case is at odds with fairness and accuracy. I'll now briefly go over the setup. We denote the domain set by X, so like the set of all people or the set of all applicants. We assume the existence of a ground truth function. So each instance is either labeled 0 or 1. We refer to an instance labeled 1 as good and bad otherwise. For example, in the context of loan decisions, a good applicant would return the loan and a bad applicant would not. Each instance in the domain is represented by the set of features capital F. For example, the features could be things like age, income, and so on. Like just for simplicity in analysis, we assume that the features are binary, but that need not be the case. The results also work when the features are non-binary but finite. Apart from the features above, we also have the group membership feature denoted by FM that maps each instance to A or D. A stands for the advantage group and D stands for the disadvantage group, which we wish to protect from discrimination. And the setting is as follows. We want to admit like a fixed fraction of applicants that we receive such that we are as accurate as possible. Do I have a question in the chat? Okay, sorry.
Sushant, you can continue with your presentation. We'll take the questions at the end.
Okay, cool, thanks. Okay, okay, I'll move on to the next. So we can basically partition the domain set capital X into different parts, and we call each part a cell. A natural way to create cells is basically based on their feature vectors. That is, two instances are part of the same cell if and only if they have the same feature vector representation. So recall we were given access to a set of features capital F, and we also had the group membership feature, and if we append that to capital F, we denote the new feature set by capital F prime. So the partition induced by capital F is denoted by small f, and the partition induced by capital F prime is denoted by small f prime. Okay. So basically a classifier assigns every point in the domain set a label from 0 to 1. And like a given partition H and admission rate R induces a classifier that we denote by HR. The score of a cell is basically the probability of a random instance in the cell being good, or in simpler terms, the fraction of good instances in the cell. Our classifier now sorts the cells of H in descending order of their scores. We then admit applicants in this order until we admit the desired fraction R. Okay. So a bit about the framework used to model the construction of simple classifiers. So as mentioned before, simplification is a common strategy employed in the construction of interpretable models. A primary source of model complexity is the number of variables or features that are used. To create interpretable models, many standard approaches try to reduce the number of variables that go into a decision. There are many ways to do this. Two of them being we could project the space of features onto a small number of the most informative variables, or we could construct a shallow decision tree that consults a small number of variables on any path from its root to leaf. These are the two approaches that this framework captures, and they follow a common principle. They simplify the underlying model by combining distinguishable applicants or applicants with different feature vector representations into larger sets and making a common decision at the level of each set. Both the approaches do not combine cells at random, but do so in a structured way. I omit details of the exact structure in the interest of time, but for example, it is easy to see that deleting a feature merges cells in a structured way that eventually halves the number of cells. Okay, so how do we measure or quantify fairness? We propose a notion in line with affirmative action that actively supports the disadvantaged group. We penalize the decisions that unfairly hurt the disadvantaged group, that are false negatives of the disadvantaged group and false positives of the advantaged group with a high weight. We also penalize the decisions that unfairly hurt the advantaged group, which are false negatives of the advantaged group and false positives of the disadvantaged group, but with a lower weight than the decisions that hurt the advantaged group. Our fairness objective aims to minimize the weighted sum of the above terms. So this is like the message of the main theorem in this section. The exact statement has some more technical details that I skip right now, and the full paper also has some variations of this theorem based on different underlying assumptions, but they have like a similar underlying message. So essentially, we try to construct a simple classifier according to the framework discussed before. If you recall, a simple classifier essentially involved merging together cells of partitions. So if we construct a simple classifier according to this framework, fairness and accuracy suffer. And this is because there exists a more complex classifier that is strictly more accurate and fair than the simple classifier. And therefore, we see that the property of simplicity or interpretability in this case is at odds with fairness and accuracy. We now come to the second main result of this work. So I'll just recall what a learning algorithm is. So a learning algorithm takes as input a database or a training set where each instance is labeled by the target variable, and the learning algorithm must identify structures in the data set and output a classifier that predicts the target variable for each unseen point in the domain set. Now, the result essentially shows that there is no learning algorithm that is fair, even approximately fair, and private while having good accuracy. The setup is essentially the same here, but we change the notation slightly. The domain set consists of elements of the form z equal to small x a y, where x is the element's features, a is the protected binary attribute. As before, we have advantage and a disadvantage group, and y is a binary label. That is the thing we want to predict. And there is a probability distribution d over the domain set x. The notion of privacy we consider is called differential privacy. Differential privacy aims to protect the privacy of each individual in a database. In this case, the database is the training set. We will first define what we mean by a database. There can be two different notions of a database. One is a finite sample with entries drawn from the distribution D over the domain X. The second notion is to just consider the whole distribution as a database. The first notion is standard in privacy literature, where databases are viewed as a finite collection of points from n individuals. The second notion is standard for statistical notions of fairness, when the goal is to ensure fairness over a large population. Notion 2 can simply be considered a generalization of notion 1, and we will therefore be using the second notion, but note that the same results and the same proof idea also work for the first notion. Okay, now we explain what it means for two databases to be neighboring. We calculate the distance between two distributions by the following expression. And if the distance is lesser than sigma for some pre-specified value of sigma, then the databases are said to be neighboring. Now the formal definition is below, but I'll skip it in the interest of time. But differential privacy essentially ensures that an algorithm will generate similar outputs on neighboring databases or distributions. Differential privacy roughly protects the privacy of an individual in the database in the following way. Changing an individual's entries or deleting or adding entries will lead to what we call a neighboring database. And because the algorithm will generate similar outputs on neighboring databases, an observer seeing the output essentially cannot tell if a particular individual's information was used in the computation or what the information is. Okay, so what notion of fairness do we use? Essentially, our result holds for most reasonable notions of fairness present in standard literature that do not allow one group to be treated much worse than the other. So pretty much all the standard notions proposed in literature would work, like demographic parity, equal opportunity, equalized odds, calibration, etc. More importantly, even relaxed or approximate versions of these notions would work. Okay, now we state the main result of the section formally. So typically a learning algorithm has access to a finite training set, which is like a finite set of points generated by the distribution D. In our setting, we give the learning algorithm an easier task and granted full access to the underlying distribution D. The impossibility result holds for even this severe restriction, which makes the result even stronger. So the theorem intuitively says that if a learning algorithm is differentially private and is guaranteed to output an approximately fair classifier, then it cannot maintain accuracy. And it cannot maintain accuracy because the set of hypotheses it can output gets severely restricted. And in particular, the set of hypotheses gets severely restricted to this particular set capital H, which is the set of constant hypothesis class hypothesis. And okay, I guess I'm pretty much out of time, so I'll skip conclusion and further work. Yeah, but thank you. I guess
Yeah. Thank you, Sushant. So there's one quick question before we move on to the short talks. Your choice of distance function is the total variation distance, right?
Yeah.
Yeah. Okay. Thank you so much. And now we'll move on to the short talks. So here we'll be having 2-minute talks, and we'll take the questions all together at the end. The first talk is going to be presented in a using a video. I'll just share my screen, and this is on fairness and interpretability. So, and it's presented by Deepak P. So, yes. Okay, I hope my screen is visible. Let's start.
The title of our paper is On Fairness and Interpretability. My name is Deepak, and this is joint work with collaborators Sanil from IIT Delhi and Joman from University of Glasgow. Fairness and interpretability, as may be widely appreciated within this community, are two heavily explored concepts within AI ethics. However, these are very distinct concepts and motivated due to different considerations. For example, fairness draws inspiration from normative considerations and political philosophy, whereas interpretability is focused on enhancing user experience and trust. These also apply more to different realms within AI. As an example, interpretability is highly significant when there is high bandwidth interaction between machines and humans, such as in fields such as robotics. On the other hand, fairness assumes most significance when AI is used to inform decisions that bear substantive importance to human lives. In this paper, we developed two conceptual frameworks to combine fairness and interpretability. The first one, called Interpretability for Fairness, or IFF, focuses on the need to explain the fairness behind the decisions. This is in contrast to usual interpretability that seeks to explain the reasoning behind the decision and is not informed by fairness as such. We propose that an IFF system should publicize the fairness values that it seeks to adhere to and provide explanations that outline how the decision is a reasonable fallout of adherence to the fairness values it seeks to adhere to. The second framework, called Fairness and Interpretability, proposes that both considerations be simultaneously achieved in the system. In scenarios where there is a deep conflict between them, making it infeasible to achieve both, we propose that fairness should not be compromised and that the user be informed that a reasonable explanation cannot be found. We hope that these frameworks will help shape the discussion and debate around how fairness and interpretability can be brought together meaningfully towards deepening ethically aligned AI systems.
So that's the end of the talk. We'll now have the second short talk, which is a material lens to investigate the gendered impact of the AI industry by Anupam Guha. Anupam, the floor is yours.
Thanks, Shivika. Is the slide something you guys will share, or may I share it from my end?
You can share it from your end.
All right, 1 minute. Also,
Do you want us to share it from our end?
no, it's fine. 1 minute. Yeah. I'm just trying to share my screen.
I'll give you the permission later. Yeah, you should be able to do it now.
All right. Is this visible?
Yes.
All right. Hello, everyone. So I'm presenting this, but it should be my students Satyam and Vishnu Priya who should be presenting it. I just happen to be their advisor, but thanks to COVID issues and because everybody is geographically distributed in very strange time zones, it falls on me. We all work, at least I work in Center for Policy Studies at IIT Bombay, where we look at how various things impact society. I, in particular, work on AI policy. So this is something which is of deep interest of me. Vishnu Priya works in the social Social Science School of IIT Bombay, where she's working on gendered economic impact of technology. And Satyam is an AI researcher who is deeply interested in AI systems. Satyam right now works as a researcher in Honda, I believe. So what is the central vanity of our position paper? The central vanity is that we went through a lot of extent critique of AI, and what we found is that a very common way of critiquing AI, especially critiquing the gendered impact of AI, is to use bias, especially epistemic bias, as a framework. So what that means is that you often, for example, have works which go into how knowledge is produced in the AI industry. So because the knowledge is produced in a gendered way, you end up with data sets which are gendered, you end up with models which are flawed, and hence you end up with outcomes which are bigoted. And these outcomes are both working at a personal and a structural level. However, the problem with this lens, and this lens is extremely common, this is the lens which informs what is called the fairness, accountability, transparency framework. And this is also a lens which is used in the majority of what are called ethics councils. As of last reading, there are around 80 ethics councils in various corporations and governmental bodies which are working on AI, so AI ethics councils. And the problem is all of them are centering this lens, and what this lens sort of ignores, or not ignores, but sort of erases is, well, we have been for a long time talking about that there are data sets which are defective, which are essentially non-representative. There are models which lead to bad outcomes. And yet time and again, we see that sometimes you will have the same company where the head of their ethics council would have an opinion about these data sets, and yet the development team of the very same company, or a certain branch of the very same company headed by some research team, would be very open to use such methods and models. So what is it that we are missing out? The argument which Bishnu and Satyam make in this paper is that what we are actually missing out is a political economic framework of the AI industry. What we are missing out is the fact that it is the profit motive which has created a very specific kind of way in which work is done, the impact of which is gendered. In very short, the argument they are making is that AI enables a very certain kind of platformization, and that platformization is disproportionately affecting women. AI also is, in a very specific manner, creating certain technologies, and the effect of them is both within and outside the industry. Why cannot I move forward? All right. So the argument they're making is that, well, let's discuss platformization for a bit. The argument they're making is that piecework or crowd work, or a certain kind of crowd work called micro work, is not something that is unknown or has been unknown before AI was on the scene or before digitization was on the scene. It has always existed. But there is a reason it could never become the dominant form of work, and the factory form was the dominant form of work. And the reason was that it was impossible to surveil, to standardize, to regulate so many people in a distributed fashion before a certain set of technologies appeared in the scene, a certain set of technologies characterized by the fact that most of those technologies use vast amounts of data, most of those technologies use machine learning, most of those technologies interact with the workforce in a certain manner, which makes it possible for micro work to exist in the way it exists now. Hence, the first...
I'm sorry to interrupt you, but you're out of time. So could you just wrap it up quickly?
All right,
we can take questions later.
All right. So the argument they are making is that AI is intimately connected to micro work. that AI enables microwork to exist, and microwork in its part is fundamentally required to create the sort of data sets which feed into AI systems. Microwork is uniquely exploitative to women, and it's uniquely exploitative because it creates work conditions where work is not considered work, it becomes erased labor, and the sort of benefits that miss out in that kind of unrecognized work is uniquely harmful to women. Microwork also atomizes the workforce, makes it impossible for them to unionize, etc. And all of these effects are again uniquely hurtful to women. The paper goes into digital taylorism, surveillance, etc., etc., all effects of the AI industry which affect women workers in very material ways. And hence it advocates that if we are going to be looking at gendered impact of the AI industry, it is useful to also look at the political economy of AI, the very specific kind of economy it's creating, and how that economy is uniquely impacting women. That is all, and I would be very happy to take questions.
Yeah, so I think we'll take questions after the next talk, please. So we'll have the last talk by Nicholas Tay. I hope I didn't mispronounce your name. And it'll be on for one and all, individual and group fairness in the allocation of indivisible goods.
Okay, can you see my screen?
Yes, please go ahead.
Right. So hi everyone, I'm Nicholas, final year undergraduate at the National University of Singapore, and this is joint work with my advisors, Jonathan Scarlett and Yarzig. Our group looks into individual and group fairness in the allocation of indivisible goods. Okay, sorry. Okay, so the problem of how to fairly allocate indivisible goods is a fundamental and long-standing one in the field. And many works, both more established as well as more recent ones, have explored a variety of distributive justice criteria that broadly falls into two categories. The first, of course, is individual fairness. How can we allocate goods such that individual agents are not envious of one another? And the second being group fairness, basically ensuring that agents of certain groups, and by groups we can refer to ethnicity, gender, or professional groups, are treated fairly overall. So for individual fairness, we consider common relaxed notions of classical properties such as envy-freeness, and we consider up to one good and up to any good variance, and similar notions for the group fairness properties as well. We make use of weighted envy-freeness, which was more formally introduced in a recent work, although similar notions have been used in older ones as well. And of course, there are many applications for considering individual and group fairness. One example is in, for example, conference peer review, whereby reviewers are the goods and agents are the papers. And groups basically represent various tracks in the conference. Right? Another example is in the allocation of public resources, such as housing or slots in public schools, if you want to treat like people of various ethnicities fairly. So a natural question that we can ask is, how can we satisfy both, right, individual and group fairness concurrently? So we went down this line of inquiry with the goal to establish efficient mechanisms that can concurrently ensure approximate individual and group fairness under certain assumptions. Right? We focused on additive valuation functions and looked into three main cases. The first, we have we term it as all common valuations, whereby all agents across all groups have the same valuation function. The second is group common valuations, where agents within the group can have the same valuation function, but valuations may differ across groups. And the last case that we consider are general valuations, still additive valuation functions, but basically where agents within the group can have different valuations for a good. And we can see that for each of these cases, we have varying levels of guarantees. And if you'd like to know more details, do drop by the poster session later. And so an important point that I like to raise from our results is that there's an inherent difficulty in concurrently achieving existing notions of individual and group fairness out there in the literature. So suppose that we have some real life application that desires for an algorithm that is both individually and group fair. Under more complex settings, this may not be possible, right? Or the approximation, for instance, may be unsatisfactory. So this work basically gives us a first look into reconciling fairness at these two levels, and hopefully let us think more about looking into novel notions of distributive fairness that relies directly on the relationship between individuals and their group structures. And just to make it concrete, in our work, we propose two of such properties, proportional envy-freeness and group stability. And we show that our algorithms satisfy them as well, on top of their individual and group fairness properties. But ultimately, we hope that this opens up more avenues of research into this area. Yeah, and if you're interested to know more, do drop by poster 7 during the session later. Okay, thanks.
Thank you. Thank you for the wonderful talk.
We are going to start with a couple of exciting long talks. So the idea is that we'll have these talks for about 12 to 13 minutes each, and we can have a couple of minutes for questions at the end. So for the first talk, I think it's going to be presented by 3 speakers. So let me welcome Charles, Marta, and Leonard, and they are going to present on spatio-temporal features and shape-based prior knowledge for fine-grained classification. So let me hand it over to you.
Thank you very much, Aditya.
Can you share your screen?
Thank you very much. Let's go. Okay. So normally you should see our screen. So hello everyone. Today we are going to present our paper, Geospatio-temporal features and shape-based prior knowledge for fine-grained imbalanced data classification. We are going to speak mostly about butterfly, but also insects in this paper. So our thematic is fine-grained classification, hierarchical classification, and attention mechanisms. Our problem, which is a general problem, is a dataset highly imbalanced and partially annotated. We are dealing with the domain within the domain of biodiversity. So insects are vital for our environment, but they disappear at an alarming rate. So we give you 2 numbers, 80% fewer insects in 25 years, and 1/3 of our food relies on insects. Insect demography assessment is limited by the difficulty to gather census data at sufficient scale. Our algorithms are in deployment on eButterfly platform, which is a large-scale crowdsourcing platform, a large-scale data collection of annotated butterflies pictures, mostly in North America. 80% of animals on Earth are insects, and there are between 6 and 10 million different species. Merely 900,000 are identified. So we see here that there is a real need for citizen science with socially beneficial application. And we try in this paper to enhance fine-grained classification using different cutting-edge methods. Our dataset is organized hierarchically. So it means that each image has 3 labels of different difficulty. Distribution implies different levels of complexity for the classification task. Indeed, we have some families, then genus, then species, and a species belongs to one and one only genus that belongs to one and one only family. We can see here on the left, you can visualize how each category is balanced. And we are able to learn very precisely the family label, but much worse the genus, and worse again, the species. So as you can see here, you have the classes here, and you see that it's very imbalanced. We don't have the same number of images per class. Also, we give on the right graph here, the cumulative distribution function. Indeed, for a balanced dataset, you have a linear cumulative distribution, while it's not the case here at all. The dot lines represented on those curves show how many classes contain more than a certain number of images. So now I'm going to let Marta speak about the geospatio-temporal features that we use to enhance our classification.
So as Charles mentioned, we have this huge data set of butterfly images, and we want to use machine learning in order to automate the labeling task and figure out what species is in the image. Now, the challenge of just throwing an image classifier at these images is that butterflies are very intricate creatures, and so the differences between two species may be very fine-grained. So here on the screen, I have two images belonging to the genus Spaeria. Now, visually, they look very similar, especially to a novice such as myself. So it might be difficult for the machine learning model to tease apart their differences. However, when we look at their geographic distribution, we notice that they're quite different. So one of the species primarily resides in the east of North America, and the other is primarily in the west. And so this is very useful information for us to know when we train our machine learning model. And so this led us to ask the question, can we use where and when a butterfly image was taken in order to improve our image classifier? So many groups have considered this problem before. One approach that was developed takes an observation, it takes an image of the observation as well as the geocoordinates of where the observation was taken, and it trains a neural network on them jointly. Now, the drawback of this approach is that at test time, when you receive an observation, it needs both an image and coordinate information, which might not always be the case. The second drawback is that if we have a lot more spatiotemporal information that don't have images to go along with them, we can't learn from that. So a second approach was recently developed that takes a more Bayesian perspective. So what this group did is they trained an image model and a spatiotemporal model separately, and then combined the predictions at test time. So this method overcomes both of the drawbacks that the previous method I talked about has, and it's also been used to successfully predict birds and other animals. So this is the approach that we used on our butterfly data set. So during our training procedure, we trained two separate models. The first is an image classifier where we take in an image of a butterfly, and our goal is to predict what species of butterfly is present given the image. And our image model for this process was a ResNet 50 convolutional neural network. The second model that we trained was a spatiotemporal encoder, where we take the spatiotemporal features of an observation, and in this case, we considered the latitude, the longitude, and the date. And the first thing we did was we transformed them using sine and cos functions so that the coordinates wrapped around the Earth and the date wrapped around the calendar. We then passed them through a spatiotemporal encoder consisting of a stack of fully connected layers linked with residual connections. And our goal was to predict what species is present given those features. So our goal with the second model is to create a distribution of what species can be found at a given date and time. Now at test time, we did something a bit different. So when we received an observation, we would pass in the image of the observation through the image model and the spatiotemporal features through the spatiotemporal model. And then we would take the outputs of both networks and multiply them together. Now, what this allowed us to do is treat the output from the image model as a likelihood and the output from the spatiotemporal model as a Bayesian prior. And so when we multiplied these two vectors together, we would get the posterior probability of what species is present given both the image and spatiotemporal features. So to evaluate our models, we considered two metrics. The first is microaccuracy, which is the total number of correct predictions over the total number of observations. And this is a good reflection of how species are distributed in the wild. The second metric we looked at is macroaccuracy, and this is the average of individual species performances. So this metric considers common species with an equal weight to rare species. So we find that when we consider spatiotemporal information, in addition to our image classifier, we see boosts of 2% in the microaccuracy category and up to 6% in macroaccuracy category. So even though everything benefits from considering this spatiotemporal information, rare species benefit more.
Now that Marta talked about the geospatial temporal data, I'm going to talk about two other innovations that we added to improve the performance. The first one is about leveraging the taxonomy of each species using hierarchical classification. And the second one is to use segmentation and attention mechanisms, since we are dealing with fine-grained pictures in a very detailed environment. So I'll start with the taxonomy. So as you can see here, when you want to classify species at the species level, in fact, you end up with a lot of very similar insects. So all these three butterflies that you can see in, sorry, Charles, can you go? Yeah. All the species you can see are very similar. So this is fine-grained. And sometimes you are not sure enough to classify at the species level and you want to stop at the genus level. So to enforce this, we need to specify a loss that can take into account how much you are certain. And we want to leverage this also, that if you are certain about a genus but not the species, then you have to render the genus. And we want to preserve the flat classification while taking into account the underlying hierarchical structure. To do this, we designed the weighted cross-entropy loss, where we took into account that we want a probability to pertain to a certain family, genus, and species. And we want a loss that would preserve the importance of the species while finding a balance to be able to render some uncertainty. Now I'm going to talk about the segmentation and attention mechanisms that we are using. So we first used the GradCam visualization tool in order to know where our ResNet models are paying attention when making a classification. What we discover is that we focus on the background way too often. Here, what you can see is that to classify this bumblebee, the network rightly paid attention to the insects, because this is where the characteristics are to be able to classify it. However, when the background starts becoming very detailed, like in this flower, it's very challenging sometimes for the network. It's polluted by the background. And here it doesn't pay attention to the Coleoptera in the center. So witnessing this, we decided to use mask RCNN segmentation as a prior. So what we do is that we pre-train the network on a small annotated data set that we manually annotated. And then we segment the whole 100,000 pictures data set that we have. So what you can see here is a butterfly that we segmented, and we are going to use this mask as additional information to design a guided attention loss. So the binary mask that we have, we add an additional penalty when training the network. So this is the loss, and the main takeaways are that once we have a mask, features outside of the butterfly mask, we are going to weight them out because the information should be on the butterfly and not on the background. However, we could argue that if we make mistakes on the segmentation, it could penalize the network. So we took this into account, and such loss is not that impacted by the segmentation errors. So in the end, our performance can go up by up to 4% using the segmentation and the hierarchical information. So it turns out that this is very helpful, especially when we build networks and models for a crowdsourcing platform that cares about the quality of the annotations as well as the species level certainty. So in conclusion, our models are now deployed in the eButterfly program, and this is very helpful to gain more users, because sometimes the bottleneck is that you upload a photo of a butterfly, but you don't know the species and you don't have the expertise. And the experts are actually overwhelmed. They currently have 300,000 pictures that are not annotated yet, because it takes a lot of time. The AI can automate this and make this faster, while encouraging users to find this very funny. In addition to this, we want to advance biological knowledge using our models. In particular, we can discover correlations between bird species and the butterfly species in a given place. We can study the correlations between butterflies and where they are, for example, around a lake, a mountain, or a forest, and we can use satellite data for this. And we can even determine the plants in the background of the wildlife photos. And there is way more to discover with all these data sets. So thank you very much for your attention, and we are pleased to answer any question you have.
Thanks so much for the amazing talk. So if you have any questions, please feel free to just unmute and ask. I can ask one question I was curious about. So I was just wondering whether, so in this real world data set, is there any instance of, so some kind of change in the distribution of butterflies observed at various locations? Meaning, if you have this data set which was trained on this particular type of butterfly, which were only observed in, let's say, Africa, but is it possible that those species are now they start to appear in, let's say, Asia or something? And how would you take care of that? Because you might not have data, location data and all that.
So I can try and answer that. So I think that has happened in the past with like monarch butterflies, for example, just appearing in Hawaii, which is a crazy flight to take. But if that was the case, our model, at least with the geo prior, it would be wrong. But then we would flag it as wrong and then figure out that it's actually a shift, and that's an error that we need to pay attention to because it's telling us something about how species are changing over space and time.
Okay, thank you.
Another thing that can be interesting around this is that we can monitor if, for example, climate change has an influence towards the distribution of a species. And it turns out that, for example, monarchs in particular are very well monitored because it's a famous butterfly that is decreasing by thousands, and the populations are getting so small, and the migration pattern is changing. And it's clear that we have this pattern, but there is no study using wild large-scale knowledge. So we can leverage our prior network to find interesting informations.
Thank you so much.
And there is a question, Marta, it's for you. What would be the accuracy if you just used spatial temporal information?
So to answer that question, it's very bad. If we just looked at coordinates, the performance of the model is poor. It's around 10% if we look at top one, but that's what we expect it to be. Because if we receive a coordinate, for example, if we're somewhere in Central America where there are so many butterflies and we receive a single coordinate, we can't expect to get the exact butterfly correct. It can be one of many butterflies that can be in a given location. So our goal is just to create a distribution of what species can be found at a given place. So we're not looking for top one or top three accuracy with that model. We're just looking to create the right distribution. And then when we incorporate that with our image model, that's where we see the true gain with the model.
Thanks so much. So in the interest of time, perhaps we should move to the second long talk. Thanks a lot again for the wonderful talk.
Thank you.
Thank you.
So our second talk today is going to be presented by Ingmar Weber. Hopefully I pronounced it right. And the talk will be about the relative value of Facebook advertising data for poverty mapping. So hand it over to you, Ingmar.
Great, yeah, thank you, Aditya, for the introduction. So this will be a very different flavor of talk, but hopefully will still be interesting to the people in the audience. Okay, so first, just a quick shout out to contributors. So first and foremost, Masumadi, who's here at QCI, but then there's also Benjamin, Ferda, people from UNICEF, and also people from a data science company in the Philippines called Thinking Machines, who've contributed to different elements of this line of work. Okay, so in this work, we look at the relative value of Facebook advertising data compared to high-resolution satellite imagery for poverty mapping. And I'll try to explain, the different data sets and also, what is the challenge of poverty mapping as I go along. So I assume that many of you will not be familiar with Facebook's advertising data. So let me spend some time on this. So what you're seeing here is a screenshot of Facebook's advertising platform. So this is publicly accessible. It's also accessible free of charge until you get to the point of actually launching an ad campaign, right? So I'm sure you're familiar that Facebook makes most of its money through targeted advertising. And so here I'm at the step of launching an advertising campaign where I can target who should see the ad that I'm about to launch, right? So here, so far I've selected a particular age. So far it's quite generic, age 13 and above. I've selected a particular gender. Here I've selected a man. Then I've selected things that are more specific. So Facebook has information about countries that somebody has lived in. So here, oh yeah, should have clarified. So the location you see on top is in Doha, Qatar, right? So this is just part of Doha. So it's sub-city resolution. So it's a 1 kilometer radius 2-kilometer diameter in Doha, right? And here I'm targeting Facebook users in this location who are men who used to live in either India or Nepal. And then, and this relates to wealth, are using an Android device. So later I'll discuss more about this, but in a nutshell, whether somebody uses an iOS device or an Android device is a strong proxy for wealth. And you can be even more specific in targeting people who have an iPhone 12 or something or Galaxy S20 or so. And then crucially here, Facebook tells me how many people match these targeting criteria, right? So I get this information for free. Again, this is publicly accessible. It's available for free before I launch the ad campaign, right? So it's a sort of like a real-time digital census over Facebook users, right? I can query Facebook also through an API. I don't have to do this manually, but how many of its users match certain criteria, right? So this is one type of feature that we use in this work. So in particular, whether somebody uses an iOS device, or rather how many iOS device users there are in a particular area. And then another feature which turns out to be very predictive is Facebook penetration itself. Just knowing the total number of Facebook users compared to the total population also turns out to be a strong predictor of relative wealth. I'll get back to that later. Just to show you some sort of plausibility things first. So this is a public demo. So I invite you to have a look at this later. So here I'm showing the distribution of iOS devices across New York City. So in Manhattan and sort of Midtown, about 90% of Facebook users are using iOS devices to access Facebook. Whereas in the Bronx, it's only about 40%, right? So you would probably rightly assume that there's a higher concentration of wealth in Manhattan than there is in the Bronx. And you'd be correct, sort of, right? But this, of course, now in the case of New York City, you have open government data, you have census data, right? You don't need this. It's just a toy example just to show you that you get something plausible. But you can do this anywhere in the world. So here's another data visualization. In this case, it's for Lagos, where you sort of see that on Lagos Island, where the government is located, you have a comparatively high percentage of Facebook users using iOS devices. In this case, it's about sort of 15%, whereas in sort of other parts of Lagos or the suburbs, this drops to about sort of 5%, right? And so now you'd be assuming that probably the wealth in the sort of government area is, or the income is higher than in other parts of Lagos. Okay, so this is one type of data. So the device access, as well as just sort of Facebook penetration that we're using. The other type of data that we're sort of comparing against is satellite imagery. So for this particular study, we're using data that was obtained through a Google Static Maps API at the zoom level of 17. So here I'm just showing an image of sort of what you can see. So this is not the highest level that's available. I think this is sort of a 19 sort of or so, but it's still considered sort of high resolution compared to sort of lower imagery that, that might only have like a sort of 10-meter resolution or sort of. So this is, let's say, roughly like maybe like a meter per pixel, more or less. This comes from Maxa or Digital Globe. We don't know the date precisely. This is not part of the data that's provided through the Maps API. And here we collect this for certain patches, not as of around sort of between 10 by 10 kilometers or 5 by 5 kilometers in rural/urban areas. Not how the locations are selected in a second. So for satellite imagery, the question is now, how do you map this to features? I mean, if I just talk, percentage of Facebook users using iOS, that's simple. Here it's not so simple, although it's also not very, very difficult. So what we're using here is not our work. I mean, we're just sort of, we're just, reusing what others have tried, which is a fine-tuning an existing CNN that's trained on ImageNet. And so here it's being fine-tuned on the task of predicting, so using daytime satellite imagery to predict nighttime light intensity. So what others have found is sort of so that if you look at how much light is being emitted at night from a location, that's a strong proxy for economic development, right? So at the very least, you need electrification to see light being emitted at night. But also, roughly speaking, the more light, the more economic activity. So if you can predict light from daytime imagery, that's sort of like a first order proxy. So this gives you like a fine-tuned network, and then you chop off the last layer, and you have a system that extracts features, right? So these sort of features that are supposedly useful for predicting night light, hopefully they are also useful for predicting different levels of poverty. So this has been shown by others so before. So in this case, we're using about 4,000 dimensional feature vector. So now we have sort of these two different sort of feature types. So things derived from Facebook, things derived from satellite imagery. So now, okay, so how do we sort of train a network or train a regression model? In this case, we're using data from USAID. USAID has this program called the Demographic and Health Survey, DHS. We're using data from both the Philippines and for India from our work. So what they do is they sample in these countries a set of representative locations, and in these locations they sample a set of representative sort of households. So think of it so these locations are called clusters. Think of this like either as a village or a small sort of neighborhood, and in each cluster they sample around 40 households. And then in every household they would ask a set of questions related to asset ownership. So you know, do you have a fridge? Do you have a television? Do you have a motorcycle, etc., etc.? So now they have sort of this, you know, this battery of questions that they ask, and then they collapse this using principal component analysis to a single variable or a simple value. Like a large positive value means a lot of wealth, a lot of stuff is being owned, and a large negative value means, you know, very, very little things are being owned. The value of 0 is basically average. So they ran this data collected in the Philippines in 2017 and India between 2015 and 2016. In both countries, this is the most recently available data. So this is the training data, right? And now we are using satellite imagery, which is presumably from somewhere around sort of 2019, though we don't know exactly, and also Facebook data from 2019. There's a bit of a mismatch here, but this is as close as we can get. Just a few words on the ground truth. The ground truth is actually not gold standard sort of. So there are different types of noise that keep you from also getting ever like a perfect prediction. So one is just sort of sampling noise, right? Just, I mean, it's not exhaustive. You just pick 40 households, right? And so if you were to pick another 40 households, you would get a different answer. So this sort of, to get a sense of this, we come up with some sort of bootstrap estimates, estimating that sort of the ground truth with itself would only have an R squared, sort of would only explain about sort of 96% of its own variance. But then there's a bigger source of a noise that's deliberately introduced by DHS through spatial perturbation. So they don't actually report the precise geographic coordinates, but they perturb it to protect privacy. Right? And so this, through experiments, we sort of show that this actually leads to quite a bit of degradation in terms of how much sort of the ground truth explains of its own variance, if that makes sense. And if you can put this together, you get sort of like an upper bound that, you know, no system out there in the world should be able to explain more than about sort of 84% of the variance, both for the Philippines and India. So just keep that in mind. Sort of, so 80.84 is an upper bound, just given the inherent noise in the ground truth. And you mentioned we're doing this both for India and the Philippines. Philippines has a slightly higher GDP per capita, both absolute, but also in terms of purchasing power parity. And crucially, Philippines has a higher internet penetration, about sort of 73%, about 41%, and a much higher Facebook penetration. So Philippines is about sort of 2/3 of the population is on Facebook, whereas in India it's only about sort of 20%. And also here I'm already flagging this gender discrepancy, right? You can see that in India there are far more men than women on Facebook, whereas in the Philippines it's balanced. If anything, there are actually slightly more women than men on the platform. And model fitting, just very, very simple sort of regression setup. Right, so the task is you want to predict the wealth index with a bunch of sort of features, try to, you know, different sort of regression models. In the end, especially for the satellite imagery, rich regression worked best. So basically it's a linear regression with a regularization term. Nothing really fancy going on here. Okay, so how well does it work? And also importantly, how do these two different data sets that, you know, capture very, very different things, like sort of compared to each other. So let's start at the Philippines, right? So if we just compare only using Facebook data, which is a 23-dimensional vector, with using only satellite imagery, which is the 4,000-dimensional vector, we get a somewhat similar performance in terms of cross-validated R square. If you add additional features related to the sort of regional dummies and things related to population density, both of them increase, and sort of satellite imagery is again slightly on top. And if you put everything together, you sort of get something that's better than any one thing. Okay, so but at least it's sort of somewhat similar performance, between these very different sort of features. But now, if you disaggregate by urban and rural areas, something interesting sort of happens. So first, you'd see that the performance drops. This might be surprising, but actually is expected, because now it's a harder task. So now if you're looking at just urban clusters, then, I mean, put simply, urban areas are have higher income than rural areas. And so there's less variance to be explained with to begin with, sort of. So it becomes a harder task. But now for urban areas, Facebook does better, and for rural areas, sort of the satellite features perform better. And then this holds once you bring in additional features, this pattern. And if you combine everything, you sort of you get the best of.
I just wanted to mention that it's nearly time. So if you wanted to wrap up.
Okay. Oh, sorry, I was so slow. Okay. So long story short, so in the Philippines, Facebook works better in urban areas than rural areas. In India, satellite imagery always works better. You can also do this model for demographic disaggregation. So you can make poverty models just for self-declared highly educated people or self-declared not educated. You can make similar predictions for disaggregated by gender. If you do this, you run into issues related to gender gaps, related to the Jackie Robinson effect, where those women on Facebook are not representative at all. So Jackie Robinson was the first African-American baseball player. And so for him to make it to the major league, he had to overcome lots of systematic racism. So he was, exceptional. And so if you were to generalize from him to all African-Americans, you would think that all African-Americans are exceptional baseball players. Anyways. Other countries where Facebook might help is Indonesia could be a promising area. Okay, last slide. Facebook is a bit challenging to use in low population areas, so they don't give you estimates lower than 1,000 people. And these models are unlikely to have long-term stability because Facebook usage changes. I mean, but satellite imagery probably also changes in terms of how things look like from space. There is an abuse potential for monitoring at-risk populations. So for example, I'm originally from Germany, and you can use these platforms to create like a map of where in Germany people are interested in Jewish holidays, right? So that's something sort of definitely to worry about. The temporal, if you can sort of, you probably can't catch sudden wealth losses. So if people become poor, they probably don't sell their iPhones immediately, but if they suddenly become rich, they might upgrade their phone. So in that case, you can probably catch that better than with satellite imagery. Unlike satellite imagery, you tap directly into asset ownership. You can disaggregate, you can have predictions for different demographic subgroups. I'll stop there and happy to take any questions. And sorry if I ran over time. Thank you so much.
Thank you so much, Ingmar. That was very interesting to listen to. However, right now, in the interest of time, we'll keep the questions for poster session. And so let's move on to the next part of this session, which is a series of short talks. So for that, there are some pre-recorded talks. So I'll just share my screen, and so we'll be streaming the video. So I hope this is visible to you.
Hi everyone, my name is Shagan, and today I'll be presenting our team's work on assessing the influence of political leaning on COVID-19 media coverage. So news coverage has played a big role in getting across information to the public during the COVID-19 pandemic. However, given the increasing polarization of US news media, we wanted to examine how the political leanings of different outlets have affected their coverage of the pandemic. So we collected 400,000 articles from 171 news outlets along with their associated political leaning ratings. Using this data, we analyzed differences in intensity and content of coverage and the framing of government officials and organizations across the political leaning spectrum. This graph represents the intensity of COVID-19 coverage per political leaning as a fraction of total news output. We find that center-leaning outlets dedicated more coverage to the pandemic during the early months, and that they shifted to right-leaning outlets in April. Next, we use topic modeling to examine differences in content across the leanings. This figure represents the percentage of articles for each of the 15 identified topics. We found that center-leaning outlets focused on economic impacts of the pandemic, so for example, topics 2 and topics 12, while left and right-leaning media appeared to mirror each other, both in terms of topic proportion and content, while tackling more politically charged topics such as coverage of the president, topic 0, and lockdowns, topic 13. Finally, we measured the frequency of mentions and sentiment towards entities involved in the pandemic response. We found that perceptions of public health officials varied by individual across the political leaning. For example, mentions of Stephen Hahn were associated with positive sentiment in right-leaning outlets. This could be explained by the EUA of malaria drugs that were touted by President. Sentiment for CDC coverage was largely neutral across the news sources, while coverage of the WHO was negative, especially for left-leaning media outlets. So, to conclude, the political leanings of US news media affected their coverage of the pandemic, and this warrants further investigation. In our future work, we hope to improve our sentiment analysis, either by using contextualized language models or connotation frames to capture subtle variations in sentiment. Furthermore, we would also like to conduct an in-depth analysis to examine how support for public health policies has varied in the media across the political spectrum. And that's it. Thank you.
So thank you for listening. So by the way, this talk was presented by Shagun Gupta. I forgot to mention that before the talk. The second short talk is also pre-recorded and it will be presented by Helen, and it's based on artificial intelligence to inform clinical decision making, a practical solution, and an ethical and legal challenge. So let me again just quickly share my screen.
Hello, and thank you very much to the organisers for inviting me to come and talk to you all today. The first thing I'd like to say is thank you to John Ives, Giles Birchley and Andrew Charlesworth at the University of Bristol in England for supervising me, or else I certainly would not be here. Today's 3-minute presentation outlines my paper titled Artificial Intelligence to Inform Clinical Decision Making, a Practical Solution to an Ethical and Legal Challenge. My paper discusses the challenges of allocating legal and ethical responsibility to stakeholders when artificial intelligence systems are used in clinical decision making and offers risk pooling as a solution. A quick definition of AI to start with. Artificial intelligence may be described as machinery that learns and then acts on that learning. That description in practice may look something a bit like this. We put in whatever it is that we want the AI to look at, for example, an image or a set of medical notes. The AI system subjects it to some kind of process and then dispenses an output. But depending on the type of AI used, the process may appear as a black box. The problem here is that an observer might not be able to see or understand the process which the AI system subjects its data to. As a clinician myself, I'm interested in who would be held responsible if a patient came to harm due to a recommendation from an AI system being used. I performed legal analysis with Kit Fotheringham, where we speculated that software developing companies could be burdened with a duty of care if harm eventuated as a result of a clinician using an AI system, but that proving causation might be challenging. Therefore, that software developing companies might be protected from claims as clinicians are the users of AI systems and are choosing to use the AI's output. This makes clinicians vulnerable to negligence claims. This seemed deeply unfair on clinicians, so I explored ethical theory to understand and express why this was unfair. One key ethical theory I've explored is that of Zimmerman, who identifies prospective and retrospective responsibility. My paper suggests risk pooling as a fair answer to the challenge of allocating responsibility. This is because risk pooling allows a platform for clinical users and software development companies to discuss the use of AI systems and the risks and benefits which would arise from that use. This is because risk pooling is a prospective arrangement between all stakeholders involved in the design, deployment and use of an AI system who have a duty of care to retrospectively address possible harms which could eventuate to a patient. I'm out of time to expand on my paper any further, But thank you for listening to me, and if I can be of any service to you, then please do feel free to contact me.
Great. So for the third short talk, it is going to be presented by Rupak Sarkar.
Yeah, can you hear me?
Yes. Do you want to go ahead and share it?
Yeah. See, I can't seem to share. Yeah. So can you see my slide?
Yes.
Yeah. So I'll be presenting our paper, Social Media Attributions in the Context of Water Crisis. This was a joint work. Yeah.
Can you switch presenter view?
Just a second. Is it not? Oh, oops.
I think that's fine. I mean, we are running short
So,
of time, so yeah.
Yeah. Welcome to my presentation of our paper, Social Media Attributions in the Context of Water Crisis. It was a joint work with Shantan Mahinder, Hirak Sarkar, and Ashik Khudabaksh. Water crisis is one of the most critical sustainability challenges the world is facing at the moment. 11% of the world's population doesn't have access to clean drinking water, and this number is only projected to increase. India has 18% of the world's population, in contrast to having only 4% of the world's freshwater resources, which makes India already a very water-stressed country. And all of this has led to 600 million people facing acute water shortage in 2019. The research question we wanted to focus on in our paper was, what factors do people attribute for a collective misfortune or crisis, such as a water crisis? As our data set, we considered comments on relevant YouTube videos. YouTube is very popular in India, and many YouTube channels widely covered the topic during the water crisis. For our list of possible factors, we considered relevant research on water crisis and considered 21 broad categories. The main challenges we faced while dealing with such a noisy social media text was multilingualism and the fact that most people in India speak English as a non-native speaker. And this leads to some grammatical disfluencies, as one you can see on the right. Our main machine learning contribution was constructing and proposing an attention-based neural classifier, which was based on top of BERT, fine-tuned on social media English. Even on this challenging data set, our model managed to produce a F1 score of 62.1% on 62.01% on resolution and 71.32% on the top three resolution to top three factors. We have seen that our model is generalizable to other crises such as Flint, Michigan, and Cape Town, South Africa. And we have also seen that, unsurprisingly, government inaction is one of the topics that comes up on the top three most attributed topics in all of the cases. We hope that through our data set, further research on this topic will be able to produce much better performance, and all our data set and code is available at the link. Thanks for listening.
Okay, thank you, Rupak. So let's move to the next short talk. So this will be presented by Burala OAC. I'm sorry if I mispronounced the name. So do you want to go ahead and share your screen?
Okay, I'm sharing my screen. Let me put on video. Okay, sorry, I'm trying to look for the video. Okay, hello everyone. My name is Burala Yowuse, and I'm presenting our work, Semantic Enrichment of Nigerian Pidgin English for Contextual Sentiment Classification. This work was done with Olubayo Adekombi and Olalekan Akinsande of Data Science Nigeria. in Nigeria, the popular language is English. That is the lingua franca, but we have an interesting variation called Nigerian Pidgin English. And when people communicate on social media, when they communicate in their day-to-day language, they use Pidgin English. I'll give an instance of why we are doing this work. In Pidgin English, if you say ginger, ginger means a plant or a fruit or whatever, a spice as you know it. But in Pidgin English, that simply means to encourage someone, to uplift someone. So when standard sentiment analysis systems are being run on Nigerian related social media, where people speak in pure English or they code mix their English with Pidgin English, there are issues like this that makes them underperform. So our work proposed two things. We proposed a standard data set, about 14,000, that people can, because we want a more inclusive, when people do sentiment analysis, when they do AI, we want it to reflect who we are as a country and to be able to capture the right context. So we presented a data set that is properly labeled with open Twitter data with Pidgin English with sentiment labels. And then we did an interesting thing with Veda. Veda is a popular algorithm for rule-based sentiment analysis. So for some of the most important work, for some of the most important sentiment token in Veda, we attempted to translate them to Nigerian Pidgin. So we translated about 300 of those sentiments to Nigerian Pidgin. And one of the interesting things that happened with this is that as we can see this table, I think my time is almost off. So the difference between data that was trained for sentiment analysis on a data set that has been augmented that was trained with Veda that included Pidgin English. Obviously, it did a better job of translating the sentiment of these words. So in summary, in Nigeria, when we speak as a country, we code switch between English and Nigerian Pidgin. This work we presented a standardized data set that people can use to train better systems to answer better questions on our social media data, and a variation of Veda. Veda is standardized, and a variation of Veda for sentiment analysis. I think that is the end of 2 minutes. I hope the poster session is longer, and then we can share more about this. Thank you for listening.
The last talk is presented by Arpita, and so it is titled Learning Restless Bandits in Application to Call-Based Preventive Care Programs for Maternal Health. So let me again share my screen, and this is a pre-recorded talk.
Hello everyone. Today I'm going to talk about learning restless bandits in application to call-based preventive care programs for maternal health care. I am Arpita. I am a postdoctoral fellow at Harvard University, and this is joint work with Gaurav, Pradeep, and Milind. The motivation behind this work is improving the well-being of women during their pregnancy, childbirth, and the postnatal period, which is called maternal health. Maternal health care needs special attention because maternal deaths are unacceptably high in India, mainly due to the lack of obtaining timely information about preventive care. For ensuring timely information, a non-profit organization called Arman carries out a free call-based program called M-Mitra for spreading preventive care information among pregnant women. This program is targeted especially for underprivileged and low-income communities in India. We work closely with the organization, and the question that we ask is how to ensure that the enrolled women listen to most of the information which are sent to them. One of the answers is by providing interventions, that is a personal visit or a phone call by a health worker. Now the goal is to carefully choose the beneficiaries for interventions because interventions are expensive. It requires dedicated time of the health workers, which is often limited. So it can be provided only to a small fraction of overall enrolled women at any particular period of time. Also, the extent to which the engagement improves upon intervention varies among individuals, and it needs to be estimated. So overall, we address the problem that at each time we need to select a subset of M beneficiaries out of the total N beneficiaries, in order to maximize the total benefit of intervention. Now, we also assume that each beneficiary has an underlying Markov decision process with 3 states. The first state is the self-motivated state, where beneficiary picks up most of the calls and listens to almost all the information sent to them. The second state is persuadable state, where the beneficiary engages less frequently and there is a possibility of increasing engagement by providing an intervention to them. And the third state is lost cause, where the extent of engagement is very low and there is a high chance that the engagement remains low regardless of any intervention. So to theoretically understand the entire problem, we formulate it as a restless multi-arm bandits problem. And we propose a solution which is based on Q-learning to dynamically learn whom to provide intervention to when the transition probabilities are itself unknown. We also provide theoretical and empirical results in our paper. Thank you. Please attend the poster session for more details.
Awesome. So that brings us to the end of this short talk session. And after this, we have this poster session, and for which I will now hand over to Arpita to take it forward from here.
Thank you, Aditya. Thank you so much for chairing the session, and thank you to all the speakers for such excellent talks. Unfortunately, we don't have time for the question answer sessions. Let's do it in the poster session itself. And thanks, everyone.